Maharaja's Forest. South is Maharaja's Forest. Other main campus. Next area. Okay. So we can start, I think. Yeah. നമുക്കിപ്പോ ഇത് സ്റ്റാർട്ട് ചെയ്താലോ? നെക്സ്റ്റ് ടോപ്പിക് കണക്ട് ചെയ്തോ? ടി വി കണക്ട് ചെയ്തു. ടി വി ഒരു വൈഫൈ, രണ്ട് വൈഫൈ. Okay, that's it. Good morning to all. Good morning to all. Let us begin the proceedings without much delay. There is no inaugural session for this meeting. We are straight away moving towards the technical sessions. So without much introduction, without consuming much time, let me welcome our moderators for the sessions. Dr. Smita and Miss Steffi will be moderating the sessions today. So they will be taking care of all the proceedings. So let me invite Dr. Smita and Steffi to hand over the dais and start the proceedings.
Good morning to everyone gathered here in person and to all joining us virtually from across the institutions. It is my great pleasure to invite all of you to this one-day brainstorming workshop and panel discussion on organization of convection, tropical storms, disturbance, and extreme weather events. This workshop is convened by the International Commission on Tropical Meteorology, a key commission within the International Association of Meteorology and Atmospheric Sciences, in partnership with Kochi University of Science and Technology. Our gathering today brings together an exceptional group of scientists, from early career researchers to globally respected leaders, to share, question, and co-create insights on some of the most complex and urgent challenges in atmospheric sciences. From the microphysics of tropical clouds and mesoscale storm systems to the modeling of extreme rainfalls, lightning activity, and cyclone dynamics, we are here to engage in rigorous discussions and collaborative exploration. Thank you for being part of this conversation. To deliver the welcome remarks, now I invite Dr. Tara Prabhakaran, Chairperson of ICTM. Dr. Tara Prabhakaran, Scientist G at Indian Institute of Tropical Meteorology, is the Project Director of Cloud Aerosol Interaction and Precipitation Enhancement Experiments. Her area of research include cloud microphysics, boundary layer processes, and cloud seeding research. Dr. Prabhakaran has extensive experience in planning and executing field campaigns using aircraft and ground-based experiments. She has more than 150 peer-reviewed publications and has contributed to WMO peer review reports. She has obtained her PhD in 1996 from University of Natural Resources and Applied Life Sciences in Austria. Dr. Prabhakaran was a member of International Commission for and Precipitation and WMO Weather Modification Expert Team. He is currently a steering group member of WMO World Weather Research Program, Urban Prediction Project, and member of WMO Steering Group of Integrated Hydro Precipitation Project. She is a recipient of Anamani Award of the Ministry of Earth Sciences and a fellow of Indian Meteorological Society. I welcome you, ma'am, to deliver the welcome address.
Thank you. Thank you very much. Thank you all for joining today. Indeed, it is a great pride and privilege for me to indeed introduce you to this ICTM, which
Ma'am,
is...
you're muted, okay?
No, I am not muted. Hello? Are you able to hear me?
I
Hello?
can hear you.
Ma'am, we can't hear you.
We can
Yeah.
hear.
You can't hear me? Should I go out and again come in? Are you able to hear me?
I hear you.
Hello?
I think online participants can hear you, but the offline
Okay.
cannot.
Okay. I'll then again re-log in, or can you hear me now?
Yes.
Can you hear me now?
Yes, ma'am, we can hear you.
Okay. So again, I am sharing a presentation here. So it is my great privilege and honor to be here today to tell you something about the International Commission on Tropical Meteorology. And to know about this activity, indeed, we should initially know what is IAMAS and IUGG. So most of you might have heard about International Union of Geodesy and Geophysics. Actually, under that, there is a International Association of Meteorology and Atmospheric Sciences. This is among the 8 other associations that are under the IUGG. So, as you can see, EMS indeed it is consists of a president and several other officers. Dr. Andrea Flossmann is the current president of EMS, and actually EMS promotes research in atmospheric sciences, programs requiring international cooperation, and EMS also leads the Alliance of Capacity Transfer, and with the joint activity with the WMO and University Corporation for Atmospheric Research, that is the UCARR. And these are indeed voluntary efforts of several scientists, and actually the science is carried out by almost 11 commissions. The 11, it includes the ICTM. So in order to give you an introduction of ICTM, this is a commission which is under formation, and the commission is under the EMAS, and the commission is under development with nearly 25 experts from world over. And the main aim of this commission is to organize meetings in tropical meteorology. There are many other objectives under the ICTM, that is to enhance research in tropical meteorology by organizing conferences, workshops, and symposia, and to enhance understanding of tropical circulation systems using observations and model, and to simulate exchange of scientific ideas and international collaborations in tropical meteorology. It is to support also student scientists to attend conferences conducted by the commission. And it will also establish certain working groups and committees and joint committees with other commissions of IUGG, and to organize joint meetings, IUGG and AMAS commissions during major international conferences, and the members of the commission will work towards that as well. And eventually we will report these activities to IUGG through EMAS. So ICTM currently considers several topics, and it ranges from the cloud microphysics to the large-scale circulations and various topics of tropical meteorology research. And I'm not, actually there is a website available, and you can have a look at that website also under the EMAS. And the contributing members, currently there are 20 members that are indeed contributing to this the ICTM development. And Dr. Abhilash, who is organizing today's event, is one of the members, and this is how the members will be contributing to the ICTM by organizing workshops, discussions, as well as conferences on thematic topics. And so far our timeline actually, sorry, it has been long, it started last year, March, and there were several efforts done by the members, and we are going to have a see, currently we are conducting several panel discussions on different topics, and we will make a report of these. This is the fourth panel discussion that is taking place. So we'll make a report from these panel discussions, and we'll be communicating it to EMAS for the formation of the ICTM. And also the proposal will be presented in the upcoming EMAS IUGG assembly in Busan, Korea, in this month, third week of this month, and thereafter a meeting will be conducted to decide on the commission future activities, etc. So that is the overall action plan for the time being. And we can also look at what all happened. This is, as I can tell you, this is the fourth such panel discussion under the ICTM activity. And with the topic is organization of convection, tropical storms, disturbances, and extreme weather. It is coordinated by Dr. Abhilash from CUSAT, and we are very grateful to him for organizing this event. And we are also live streaming the event so that it reaches many other scientists and students, and it will be available. So before going into saying thank you, I want to also tell a few points on the organization of convection. Actually, this is a this is the spontaneous clumping of convection that can occur without any predetermining external perturbation. This is actually seen in many of the cloud resolving simulations that are conducted to study the storm's disturbances. And it is immensely important for the climate sensitivity and extremes. We are worried about the extremes of precipitation, extreme other phenomena or the impacts that are happening due to the extreme precipitation. And it is a large source of variability in the climate models. And observations also show that most of the regional increase in the tropical precipitation is associated with changes in the frequency of organized convection. And actually, there are further studies which also says about the Darnell cycle impact on the Darnell cycle and the convectively generated cold pools and mesoscale convective systems. And actually, it is indeed in the Darnell cycle means day-to-day forecast. It is very important as well. And the daily precipitation extremes tend to increase in more organized convective state, accompanied by increased storm size but decreased storm number. This is from a recent publication. It is actually very, very important statement that they have made. And as actually not only for the Darnell cycle, when we think about the climate, warming of the climate, and it is shown that an increase in the organization and aggregation of convection happens, and the storms are larger but less frequent, and they are more extreme. And also changes in the frequency and morphology of the convection is another topic. And daily precipitation extremes increase in more organized state. The organization is quite important in this, and daily variations in tropical extreme precipitation accumulations are very closely linked with the mesoscale organization. That is a very profound statement as well. And how the convective organization will change with warming is something that there is significant uncertainty in here, but there are a number of studies that are coming up on this, and this is indeed showing a very big importance of this topic. And actually, most of the studies that are currently, there is a very big thrust on the mesoscale convective clusters. The mesoscale convective clusters are actually several deep convective clouds plus thick anvils. And it has been shown that the intensity and duration actually of these systems, they are lasting more than 12 hours, account for 75% of the tropical rainfall, and systems traveling more than 250 kilometers account for 60% of the rainfall. And there is a strong, the important aspect is there is a strong coupling of storm dynamics and cloud microphysics. This is the challenge in many of the models. And also the process understanding is to be improved further, because all this condensation or deposition and freezing, these processes happen in very, very small areas in strong updrafts. And meanwhile, the evaporation happens in the wide downdrafts. And also the critical observations in understanding convective storm processes, we need actually the storm vertical motion information, which is indeed lacking in many, many places, especially over land. We don't have adequate observations of that. And the co-located dynamical and microphysical properties in the precipitation characteristics and latent heat, etc. These are quite important. And the model resolution and large domain and long simulations may be needed for this kind of studies. So this particular image, it is giving the mesoscale convective system precipitation fraction. And this fraction indeed shows that many of the places we have more than 70% of the precipitation coming from the mesoscale convective systems. This is a paper published in 2021. And the inferences are from the GPM observations, satellite observations. So this figure itself will talk about the importance of the topic today. And additionally, I also want to show a picture from our observations in Sholapur this May, in where it is usually it is very dry, and this is the vertical cross section of a storm that passed over our region. And the upper figure, you are seeing the signal to noise ratio. In the middle, the vertical velocity, and the down you are seeing the wind speed. This kind of information even is lacking in many places, and you see that the storms are able to last quite long. In a dry environment they have formed, and they lasted so long. What makes it so long lasting storm? And also the convective scale precipitation, it is very thin. Actually, it happens very rapidly, and the up to 80 millimeters of rain has happened from a convective cell here. So these are the observations do not adequately capture these events. That is quite an important aspect as well. So we want to discuss many of these things: observations, models, theory, and we are hoping that with the ICTM formation, we can have we can indeed increase this dialogues and understanding on several of these topics. And I want to thank you all, and especially thanks to all the early career scientists and students who are participating with interest and enthusiasm, and all the speakers and the organizers for this event. And I stop here. Thank you. Hello. 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 Hello, Brain.
Hello.
I hope.
I think they're introducing me. I think I heard my name.
Yeah.
Hello.
I,
It is now my privilege to introduce our keynote speaker, Professor Brian Mipps from the University of Miami, USA. Brian Mipps is a professor in the Department of Atmospheric Sciences at the University.
my sound has quit.
I am able to hear you.
Okay, I'm not able to hear the room, but I could perhaps just proceed.
Yeah, I am also not able to. I think they are muted.
Okay.
Mm-hmm.
I suppose I shall just begin. Huh?
Yeah, they are muted. So
Oh, I
that's
see.
why.
Yes.
Mm.
Okay.
Yeah, I
The
can
room is
see your.
muted.
I can see your screen. Maybe if you can share it full screen, or is
Tropical
it
weather
full?
especially depends on convection. So some of his research projects focus on seasonal monsoons as well as traveling weather waves. Professor Mapes also works to advance information technologies relevant to convection science. Today's keynote is titled, What Does Self-Organizing Horizontal Cloud Pattern Information Reveals About the Vertical Processes Parameters of Moist Convection? Dr. Mace, you have 45 minutes for the presentation.
Wonderful, thank you. Can people hear me and see the slides all right?
Yes, sir.
Okay. Well, all right. Yeah, I'm sorry I couldn't get there in person. Someday I would quite like to. Thank you to the organizers, the commission, and IAMAS. And it's just lovely to see the young scientists I've known, Abhilash and Tara and Ayantika, and all stepping up in mid-career stride here. And of course, the honorable other names on the program here. Yeah. Well, I'm in Exeter at the moment, and it's 5 a.m. So I had a Carolyn curry for dinner last night, and thinking of you all, and enjoying feeling gratitude that you're interested in my work, which is not very practical, I sometimes feel, but maybe the ideas underlie some practical goods, I hope. My whole career has been the age of parameterization, and the mythos of that, I would say, was that research will lead us to understanding, which will give us predictive power. And of course, observational campaigns enjoyed support kind of at the upstream end of that pipeline, and I've been involved in several and enjoyed them. Um, but it's really an engineering project, this prediction thing, and some of that was a little bit buried or underappreciated. So it's been an interesting era in science that I've come through, and I feel like the new landscape, the machine learning, the informatics, it's really information feature engineering is maybe the new way to think about things, and it's gaining us 10 to the fourth speed ups relative to the old numerical PDE solvers that required 10 grid points per feature in each of 4 dimensions. Now we use a computational degree of freedom to represent a feature and how they interact and train that. And it's just a new world, I guess. But in that, I guess observations have taken their role maybe back to just being a data resource, especially even routine ones like satellite imagery. And it's unclear, I guess, whether atmospheric scientists with a mindset like mine are how important we are to this whole thing. And boy, especially as U.S. science faces devastating cuts, it's nice to hear international organizations stepping up, and we'll do what we can here. Let's see, why did my slide advance quit? Okay, there we go. So what I'm going to tell you today is I sort of went back and forth between a critical review, I think, of pattern information extraction with satellites as the obvious case, but radar can be maybe similarly viewed. And nowadays, the models that resolve similar scales that we've been appreciating from space for a long time. And then I'll have just a little small sales pitch on my own work, which you can read. I have 2 papers in press now after kind of a drought of some years. And um, my angle on this is we should consider maybe this self-organization of convection as a well-constrained instance of ecology or economics or game theory, rather than, or not merely as, a deterministic set of physical processes which we've kind of retrofitted with statistical approaches. And hopefully that's all. I'm brainstorming here, not selling my own work too much. So I'll probably start with a sort of a critical review, I guess. Let's see how that looks. Hope people can see this. There's a lot of information in fine cloud patterns. How do I know that? Well, I take a JPEG and I zip it up, and I do it for a real satellite image, and I do it for a smooth satellite image. 90% of the information is in the small scales. So what are we learning from those small scales? It's abundant information in the new information theory sense, in the compression sense. But we're not really making any use of that, I feel, for the whole assimilation and evaluation cycle of predictive models that drives drives our enterprise. And relatedly, are we gaining understanding from those scales, meaning and implications? And hopefully that is of value just in itself as science, if not as power to predict. All right, I hope I'm still being heard here. Okay, so how we're going to extract meaning from pattern information. I'm going to walk you through 4 things here, and I'll actually skip the 4th one. So just 3. So the abstract view, which I just showed you a little bit from just zipping up a file. Information can be viewed as the opposite of entropy, the negative of entropy. And I'll just start from there, because that's kind of the new way of thinking about information, I suppose. With some asides on null hypotheses and log plots. Okay, well, here we go. I just recently learned about this paper only because I was writing a similar one. Is atmospheric convection organized? Information entropy analysis. This is the spatial entropy hour by hour of the GridSat satellite data set, an infrared imagery data set. And, it hardly ranges very much compared to, and this is a kind of a normalized entropy, where an entropy of 1 would be just white noise, pixel by pixel white noise. And an entropy of 0 would be, the whole world, all the convection in the world is one blob. And so, of course, we're closer to pixel by pixel, but noise than we are to one blob. But the authors were, very disappointed in how small this range is. But actually, I think it's quite fascinating. And they've shown here the lowest and highest entropy. Are you ready for this? The lowest and highest entropy states. Here is the lowest entropy state over the Indo-Pacific, and here is the largest entropy state. This is closer to a bunch of random pixels, certainly, and this is closer to a blob, several blobs. So I think that's kind of a useful characterization, actually, but the authors were disappointed by how narrow that is and kind of went down this theoretical track here, which was to see that this entropy decreases in an algebraic manner with a power law, and that indicates self-organized criticality, which is a special word in physics. And the classic paradigm of that is this icing model of spins. As you cool down a ferrous material, and the spins influence their neighbors, and you get this very meaningless but multi-scale paradigm of very meaningless but multi-scale structure. And so if the data here, which are black, are kind of a straight line, then that's sort of the null hypothesis, that this is meaningless structure, meaningless multi-scale structure, fractal structure or something. And, okay, sort of, the black line can sort of be fitted as a straight line with a thing, but is that the end of our science? I'm not sure. I didn't quite like the way the null hypothesis sometimes gets accepted in these studies. We build a null hypothesis and then we try to refute it, or we study how nature differs from it, rather than accept the null hypothesis and sit back and say, oh, it's all a self-organized criticality and we're done. The way we usually use a null hypothesis, and I think these log things maybe should be thought of in the same way. We often use this AR1, autoregressive red noise. This is from Madden and Julie in 1974, for instance. It's a classic paper, obviously. So our red noise is a 1-parameter model. It's basically a trivial model. It's something we want to, get beyond. It's a meaningless baseline, a baseline of meaninglessness. And we use this F-test of variance. And it's certainly a deviation of 1.7 like this is, the Madden-Julian oscillation. Hello, 50 years later, we're still talking about this. So we care about deviations of 50, 70%. Of course, that's enormous. And I think these scale-free log evaluations are often used more in a dismissive manner, where you accept the null hypothesis. This is an example. Often people do, when you have just too much data and it's everywhere, you're covering the Earth with high resolution data. It's wonderful. This is a global storm resolving model here. Well, what are you going to do? Well, take Fourier spectra by total wave number here, or zonal wave number, doesn't matter. And maybe the W spectrum is, oh, it's pretty flat. And what's a flat spectrum? A flat spectrum is white noise. Oh, the world is white noise. Uh, or, the updrafts are white noise. And other people, study oh, this is almost a line and it's almost these slopes and they come from turbulence theory. But, just notice the scale here. This is 14 orders of magnitude. So, a 100% deviation factor of 2 is this big. It's That's how big a 100% deviation is. So these little zigzags on the spectra are, 100% deviations. Matt and Julian only got 70% deviation. So anyway, these are enormous structures that we're sort of smothering with these log plots sometimes. The way I think about this is we know in our, in the science of our field, we know we have the important qualitative distinction that there's a thing called tropical cyclones, vortex-assisted deep convection, a completely different hazard, a completely different animal than our ordinary mesoscale blobs. But I have never seen a log diagnosis that where the tropical cyclones stand out. So that means, when you use crude tools, you get crude answers. And I think these logarithm, we have so much data that we want to crush the dynamic range using the convenient function of a logarithm. And there is some physics theory of that, but boy, it's a crude tool and it maybe leads to crude science. So that was my first aside, I guess, a long aside on the way to think about information in these patterns. And the other giant thing these days is thresholded anvil blob counting, I guess. When pixels touch, we call it, we pretend that means they're connected, and the pixels that don't touch aren't connected. And we label it as a convective system, a mesoscale convective system, which I misspelled, sorry. And this is just a giant, this is a cottage industry of enormous size nowadays. And my advisor, Bob Howes, kind of started this, I think, in 50 years ago. But today we just have all these data sets and the algorithms are so convenient. But to call this a system, system theory or system dynamics, it's a thing that's coherent, whose boundary really contains it. And I don't think that's quite what's happening when anvil clouds touch. But anyway, there are certainly thousands of papers now, regions, seasons, threshold, different definitions and algorithms. So how many systems are we looking at here? 23 or 11 or 1.5? It's quite ambiguous, and algorithms govern the number you get out of the computer. But what are we talking about exactly? Always bigger blobs are rarer, bigger blobs last longer in time, faster growing blobs become bigger. These are never surprising to me, almost never surprisingly. And quantitatively, we have these spectra and things. Does anyone ever go, measure the lookup graph from a research paper and say that's going to inform our engineering for sewer pipes or anything? I'd be interested to know if anyone's ever heard of that coming through. This was in my, just one day last week, this was in my mailbox. Mesoscale convective systems from India, from Northeast China, from Eastern Canada, a review. And oh my gosh, just so many of these things, and I just refuse to do them anymore. I used to think of myself as an MCS person, and now I couldn't because there's too many. And also because often they are merely descriptive. So I guess I'm looking always to see if there's an underlying important science issue that's kind of implicit in the tallying and counting exercises, and there are a few issues in there. One of them is, anvil lifetime, I guess, and that engages cloudy radiation, ice fall speed, which is just always a huge knob in these models, the microphysics of ice, and turbulence. So radiation, turbulence, and ice determine how long these high clouds last, and those are really what we're counting, in their as a system. And these hectometer and kilometer models, have to parameterize those things. So those are crucial parameterized, always subgrid parameterized processes. But perhaps more interesting, I guess, is to me is these what I would call cell adjacency controllers. What determines, given a cell, what determines whether another cell touches is close enough that their anvils touch, or happens somewhere else. And that's really driven by this kind of particle fountain model of the observed phenomenon of MCSs from Uter and Howes here. And so, the anvils are going to grow and merge just because these are particle fountains. But so the question is, why do you get cells near other cells? And this gets back to the word organization and to this way of maybe the thinking of our science as a simple form of biology instead of a hopelessly complex form of physics, where we worry about cell-cell interactions. How do you understand an organ? Well, through cell-cell interactions, how you understand tissues and organs and then entities. And those things include cold pool triggering, which is easily seen, I guess, and it's the poster child, I suppose, for cell-cell interaction. But there are also density waves that organize cells, internal gravity waves, I guess we call them, and also vortices, depressions and things. So, and waves and vortices have different kind of coupling coefficients to convection and parameterization schemes. Some will couple more to density waves, and some will couple more to vortex, mesoscale vortices and things. So, all that is. All that governs whether we end up with forced patterns or self-organized patterns. So I think this kind of cell adjacency view, just as a probability matter, I think it might be the way forward, and I'll come back to that. So when we're plotting these size distributions, this is a pet peeve from my very first paper, 1993. When we use these, again, using these logarithms, sometimes it's just a dynamic range compression. We have too long a range, and we just have to crush the data. And the one way to think is, would the square root suffice? Do we need to use the giant crusher of log? Could we use the gentle crusher of square root sometimes? So for instance, here a log plot leads to this conclusion that there's an almost equal contribution of every cluster size to the mean high cloud, and it sounds like a magical thing or a puzzle. Or if you look closer, there's a mesoscale peak here. But these are plus or minus 50% variations. And in bins which are equal in width in a log square root of area axis. I'm not sure that these words do justice to this thing, and vice versa. And this was, when I was a young, ambitious scientist, and here's another young, ambitious scientist over in New York, and we released our papers the same year. And here, I'd say, these distributions are what they are, and they just fall off. The smallest things are the most, and everything below that is just falling off. But when you take these logarithm binning, you get, a mesoscale peak, and now you have a whole what's happening at 100 kilometers to make a peak? Well, it's only because of the logarithmic binning, perhaps. So anyway, just the cloud and aerosol people are careful about this kind of notation here: dA dx, d area, d square root of area. Sometimes I think they have a nice notation here for how to think about area, volume, mass, number, distributed by size, squared size, cubed size, etc. So And all that is just a long aside. I guess I'm indulging in my pet peeves here in late career. Forgive me. So this work is getting a real resurgence because we now have models that are directly comparable to satellite observations. And there are some key points, I guess, emerging. This is from MCS MIP, where 10 feature trackers are used on multiple data sets. And I think we can say that models tend to underestimate MCS precipitation amount. So maybe, yeah, and then they overestimate intensity. I wonder if these are both really facets of one thing, that this definition of MCS as a connected anvil means that if the ones they do have are raining too much, and they aren't big enough because the anvils aren't big enough or something. I'm not sure, but again, I feel like the real issues are coded here, or hidden, or buried. Anvil lifetime and cell adjacency processes are really at the heart of this. Um, Above and beyond the MCS counting is the characterizations of the organization, which are also, so many papers, so many algorithms and things. And, just one example here. Here are 17 organization metrics. And this is from a literature called self-aggregation, and often just organization and aggregation are sort of interchangeably used. But, these are 17 morphometric algorithms, pattern describing algorithms. Of convenience, usually they're kind of convenient things you could calculate. So here's sky and COP and IORG and there's all these different things, and these are the correlations among them. And there's more red ink than blue ink here, but you wouldn't say there's one thing called organization and we're measuring it in 17 different, slightly different ways. We are measuring 17 totally independent aspects of form just with arbitrary algorithms. And we have no idea how that relates to function in the form function sense that biology uses things. We measure these aspects, but we don't have any idea what they mean really. In terms of the efficiency of convection or doing its job, or how this one's going to overcome this one, or vortices versus waves. We just have no sense of where these things lead. So again, it's a sprawling literature, but I think just so untidy, I hardly agree to review it anymore. I just wanted to give a quick shout out as well in these things, just Mitch Moncrief and others have been just holding this torch for a long time, that organized convection is a separate thing, and his paradigm has always very much been two-dimensionality, a collapse to two-dimensionality, this slantwise layer overturning idea that he has. And there's a mathematical model for that. There's a mathematical closure you get from insisting on two-dimensionality, and he's been trying to work that into parameterization in GCMs for just a long, long time, and I appreciate that, just beating the drums for we need something other than random plumes, and because there are upscale heat and counter gradient momentum transports distinct from diffusive down gradient mixing by unorganized cumulus. So that's just one more paradigm, I guess. And my own one small contribution to GCM code ever was an organization scheme. And, consider reading it, I guess. As usual, I had the discussion is more interesting than the scheme, which was just one variable instead of zero to reflect multiple positive feedback mechanisms, cell-cell interaction mechanisms. And, when it rains, it pours is sort of the shorthand of that. On the other hand, numerical schemes hate 2 delta X noise, so we don't want cell-cell interactions that put a bomb of latent heating at one grid cell and not the next one. So the engineering compromises, already intrude on getting it right in that way. So anyway, and the careless summary of this would be I invented a cold pool scheme, and Sung-Soo Park with his Unicon scheme really took that well and gave it a big Greek letter omega, which I admire. One more way that people get pattern information is characterizing little scenes or tiles in imagery. This is more modern and machine learning oriented. There's a supervised approach. Some of you have heard of these sugar, gravel, flowers, and fish work out of Europe. This is all shallow cumulus patterns. And there's an unsupervised approach by Leif Denby that I admire, kind of coming in the other side. And so you end up with classes, but you don't know what to call them. But I'm not going to go into the shallow clouds so much. This is more of a deep convection session here, I think. So let me go ahead and just sell my own recent work a little bit here. I'm trying to view pattern as an ecological problem. And what do I mean by that? I mean, so I'm not offering a formula or even necessarily a way forward. It's more a way of thinking. It's a way I appreciate the problem better as I read and think about it, is to borrow, as I say, more from biology or eco-sciences, economics and ecology, eco-sciences. And these are rich paradigms of uncertainty. With uncertainty at the core, unpredictability is just at the core. That's why it's a real game. The agents are contending through strategies, and outcome is uncertain, and that is why it's an interesting game. And that's just a nice paradigm. The uncertainty, the unpredictability are right there in the formalisms that we use to think about those things. And there's a few examples where people have tried to borrow the ecological idea, the Lotka-Volterra equation, where foxes eat the rabbits. And we're not talking about big clouds eating small clouds. And we're not necessarily even just talking about, they compete for food. And that's yeah. So anyway, we can go a little deeper than those, although I acknowledge and admire those early approaches as well. So, of course, this is a simple old nut of an idea. Here's Darwin sitting and pondering. And, nothing in mesoscales makes sense except in the light of evolution is my new credo. Mesoscale patterns, they're not really necessary. They're possible, but they're not necessary. I've enjoyed this painting which was commissioned by the Weather Bureau in 1954. What are we going to see someday when we launch a satellite? Well, we know we're going to see cumulus arranged in streets down in the tropics, because we've been down there and there's clouds in the sky and the trade winds. And we know we're going to see the Norwegian cyclone family and frontal model. So let's paint that in. Are we going to see a thing called mesoscales? Well, only maybe, only maybe in Canada where the mountains cause it or something. And then we just get tired of painting mesoscales and so gave up on the mesoscales. And except for one hurricane, by the way, do you see over here by Puerto Rico, there's one, they thought hurricanes were just kind of one giant rotating cumulus cloud. So anyway, that was an interesting view, and it shows you that mesoscales are not necessary. They're impactful, but they aren't playing a structural role in the system like, equator to pole transport or uniquely vertical transport. So anyway, we haven't known how to wrangle them. They are important for predictability, of course. For instance, the competition of proto-tropical cyclones versus non-rotating convection. That if one wins, then you have cyclones, and if the other one wins, you don't. And I noticed I enjoyed this AI-written image here from your brochure. In fact, there's your vortex assisted and your purely buoyant convection right there. And either one of these can do the job of convection in the climate system. You can have Earths that are all about rotating convection vortices, and you can have Earths that are, just popcorn. And the difference between those turns out to be merely a different boundary layer scheme. Imagine that. So these important biases like density profiles, how are those related to these pattern differences that jump off the page at you? Well, that's the question. That's the title of the talk here, I guess. Yeah. So anyway, how does a different boundary layer scheme if you get you from this world to this world? But both of them have a perfectly otherwise Earth-like climate, broadly speaking. So sometimes I think, so let's talk game theory for a moment, just to put your minds in a game view. Let's imagine we got A/B testing here. The game is to lift buoyancy the most. That is convection's job. But of course, subject to mass continuity, and mass continuity, brings in inertia. You got to get air out of the way, and that air has inertia and all that, right? So let's just think of this competition between a wider blob of buoyancy here in color, and the white, I think, is pressure. And so here's a wide blob of buoyancy, and here's a narrower blob of buoyancy. And you can see the pressure above the wider thing has more contours. So the wider thing has more pressure drag. And but the narrower thing, on the other hand, will be eroded by mixing. So you can puzzle which one is better, wider or narrow. If it's too narrow, the entrainment will get it. If it's too wide, the pressure drag will get it. And all that gets you thinking that's very physics, deterministic physics. And then just hoping to make you laugh here. Don't forget there's a third strategy called the old 1-2 punch, where, it's not an independent A versus B. It's the strategies involve interactions possibly. So, it's just hopeless that we're going to get this from a small family of rigidly deterministic structures. So the question is, are conspiracies like that, complications like that, is it unlikely that the old 1-2 will happen, or that waves and convection will get into resonant arrangements? And the answer is, in an evolved system viewpoint, not at all unlikely. In fact, inevitable. We don't know what complexities will arise, but we know that when they do, they'll be better than the simple things. So one of my favorite evolutionary philosophers here says, don't mistake a failure of imagination for an insight into necessity. And he also is the one I learned this phrase, Occam's broom. People use Occam's razor. Oh, that's A is simpler than B, and therefore it's a better theory of what's going on in the world. That can be a way you sweep untidy things under a rug. Occam's broom instead of Occam's razor. So this is the kind of thinking I've been doing these days, and just want to show you one or two examples. And I think ecological succession after a reset is the most revealing. Is what ecologists just find the most instructive, is a succession. If you have a complex climax or equilibrium ecosystem and you observe it, your observations are ambiguous about causality. You don't know what's causing what when you have this multi-layered, multi-tiered thing that's chewing away. Radiative convective equilibrium. You can observe it and you can measure correlations between things, but you just don't learn about causality. You don't understand the system. But if you have a clean slate and things grow in a succession process, then you learn so much about how these things interact. And I think that daily convection over land is our version of that. So, daily convection over land, and actually downstream evolution over the trade winds in the shallow convection realm. So here's shallow cumulus, coming offshore from Peru over the Southeast Pacific. And, in a few days, you go from the simplest thing to much more organized things, likewise off the east coast of the cold continents. That's cheating a little because the depth also rises. But let's think about deep convection here. Every night, think of South America here. Here's Colombia and Amazonas state of Brazil. Every night the convection dies down, the sky gets still, the sun comes up and begins heating the land. So here you go. You start growing these cumulus clouds. 4 hours later, there's winners and losers, and succession process is starting to build deeper and things, and cell-cell interactions are apparently making it quite clumpy. And we just, every day there's another data set of this. We have the amount of data we have from years and years of satellites staring at this. Uh, Here's a suggestion that when in the morning the clouds are clearly rather sheared, uh, in the same amount of time, maybe you get to more organization that way. So we just have so many instances of this. Why don't we study them in a systematic way? So what I tried to do in a systematic way here is, again, South America, which I like because it's a large, fairly homogeneous lowland in the middle here for deep convection. Of course, the mountains can jumpstart mesoscales, and the coastline can jumpstart the mesoscales. But out here, maybe the daily succession is we have maybe many instances of daily succession. This is one. Probably the video will work poorly on Zoom, but I don't know. I'll let it run for a moment. On YouTube, you can come back and scrub it and repeat it. But what I've tried to do to formalize this is to upstream of the science of mesoscale convective systems was this cell adjacency probability. I wonder if we can measure that here in South America. So again, here's the east coast and west coast of South America, and instead of looking for connected anvils and calling it a system, I looked for cells, which are local minima colder than -40, and then we just talk about the probability of the cell at t+1 given a cell at t equals t at the center. So you do a composite probability of cell adjacency. This is in my paper in press there, and it's on archive if you want to read it. So here's the result of that. And these are from a couple hundred daily succession exercises. And this is the probability of a cell, a map of cell probability given a cell at the central point at a base hour B and at a lagged hour H. So these are 1,000 kilometer square areas. The diagonals are the instantaneous logarithmic probability of cells. So those are just, centered things, of course, and positive definite. But off diagonals here, we have the lagged conditional probability. So over here, we have the probability at 23 UTC of a cell occurring given that there was a cell at this point at 14 UTC. So you can say when there is a cell, it tends to make an enhanced probability of new cells around it. But as time goes on, there's actually a reduced probability of cells, and that's maybe from shading of the anvils and the cold pool, whatever it is. And that central thing expands. You could measure probably a rate of expansion of this probability or it's frequency, but we interpret it as probability. So anyway, that's a fun exercise empirically, and we can sort of idealize that here with radius and time and this conditional probability factor, enhancements of probability. We could sort of formalize this a little bit. And, this is, so this is my revealed horizontal pattern information. But it's a probability. So that's not a physical process yet. It's an observed frequency, turn it into a probability. But, how are we going to, the science frontier is to understand the processes behind it. But anyway, if you take this probability kernel and iterate it in a sort of a numerical game with random numbers, a Monte Carlo exercise or something. Uh, you'll find, and again, this is in the paper, so I'll leave you to read it, but these squall lines, which are in a possibility from this probability kernel, they take tens of hours to discover that they can exist. You got all these kind of ordinary convection all around, but it takes, in this case, 60 hours for this system to discover, oh, a squall line is a special configuration that is possible. And then once it's possible, it tends to suppress the other things, and you end up with it. But it takes time. The random things are easy to form, and special things take time, but then in the end win. So that's the kind of games I've been playing. Also here in my other in-press paper with Wei-Ming Tsai, and he had a result that I think can only be understood through this evolutionary kind of thinking, which is that hardship breeds hardiness. And what he did was use a cloud resolving model, doubly periodic, and do a kind of a succession experiment. So this is time here, and this is sort of like latitude. It's the one dimension of a square cloud resolving model. And what we do is just switch on shear in 1/3 or 1/2. We just switch on the shear in part of the domain. And I'm showing you kind of the zonal mean rain rate here. The east-west direction is averaged. So this is like the y direction. But anyway, you can see when you switch on the shear, suddenly, it's terrible for convection. All the clouds here, when the shear goes on, oh, they die. I mean, shear is terrible for clouds. But after a while, a sheared belt is able to develop these squall type systems that go on to suppress the rain in the unsheared areas. And they just, it ends up raining more. So initially, of course, less rain because shear is bad for clouds. But turns out a bad thing for clouds is forces the convection. How do we say it? The convection evolves to live with the hardship, and the hardier thing that evolves outdoes the ordinary convection. We have the other thing we do is remove auto conversion processes. This is purely hardship. It's just terrible for a cloud to say it can't rain. But when you do it, somehow transform into another type which overcomes that. And you end up with, again, more rain in the hardship region, more rain in the hardship region than in the ordinary region. So, all right, I'm wrapping up here. Just want to come back to what's at stake in this new kind of thinking, ecological sort of thinking, or, what's at stake in rethinking all this. One is that beautiful information-rich data sets are going to waste. Satellites, amazing, high resolution, huge expenditures on them because in real time they have so much value. You've spent a lot, so then the data are well quality controlled and stored. Now that there's just huge archives of this, and the computers are now capable of wrangling that kind of amount of information. And it's just, I think, an underutilized resource, this configuration information, pattern information. So if we could somehow learn to transform pattern into something we care about more, like density profiles, I guess, then you could assimilate that, and it could have a place in NWP, I guess you'd say. And the other thing at stake is really conceptually, and that leads to research opportunities. So I made a vertical scale here with physics at the bottom, which many sciences envy physics, and statistical mechanics is kind of its complex frontier. And way up here is, biology of life on Earth, which is grand, but little, rather high-minded. Below that, I would say, is this ecological science. It's biological, but it's groups and guilds and stuff. And below that is maybe a thing in the middle here. I've seen called process ecology. It's sort of how we think about economics, social complexity, game theory. And down here in physics envy land, we want to find solutions to problems, and there's some unique or optimal solution, and there's equilibrium or criticality, or it's weakly deviation from equilibrium, or asymptotically approaching equilibrium, or something like that. Those are the virtues and ideals down here. Up here in biology, we know it's hopelessly non-unique. Why do I have 5 fingers instead of 6? Historical accident, right? Um, it's just mutually contingent life strategies, struggling through time and muddling along between setbacks. It's beautiful, but you can't exactly predict it or anything. And maybe somewhere in the middle, where does gravity, sorted fluid dynamics, convection, covering our broad Earth, where does it fit in on this spectrum here? And are we maybe missing opportunities if we insist on only treating it in physics ways? And it might be an opportunity just to appreciate the world better, even if we don't exactly solve a predictability problem or something, which might be a silly impossibility anyway. Anyway, just for those of you who do envy physics, maybe consider, looking upward a little bit toward these appreciation sciences like biology. So that is all I have for you, and I'll quit. And I hope the timing went well. I got a little bit out of touch with the clock.
Thank you, Professor Mates. You opened a lot of doors for us actually, and you propped our imaginations. Thank you for the talk. So now I think we'll have a quick discussion, maybe 3 questions from the audience, if anyone want to interact with Professor Mates. Those who are online also, they can ask any questions if you want.
Yeah,
Hello, Brian.
hello.
So it was really wonderful listening to you, and like how you presented the basics and then went on to say that there is so much information in the satellite images. Really, we need to capture from there and then translate that information into the models, like what we get from there, and improve the models. So like, can you give your views how that can be done? Like, we have techniques of AI ML now, but then how to include it in the models?
Well, all the way to models is and what do we mean by models? Because now
Climate.
AI is data models. These data models, empirical, high dimensional empirical models, AIFS from the European Center and stuff. Maybe we don't need to go through the numerics and physics track as much anymore, right? So one way into the models is just have your models be data models, AI ML models, and now the data goes right into the model because you don't have to convert it into a physics formula or something. So that's a question, I guess, is whether the physics formula traditional parameterization is the future, has a place in the future or not. So that's one possibility. And but it is
like
great that
replacing the physics you are telling with the information that we have, right? The cloud physics, the convection.
yeah, but not and then that's unsatisfying, right? So of course, as soon as I say it, that's unsatisfying. But things like the ice fall speed parameter or something. Let's say there's a knob, right? Okay. In a way, you could infer it from the patterns that emerge when you change it and make those patterns match the patterns. Maybe that's just back to plain old MCS counting, right? As MCS MIP shows, the models the physical storm resolving models, kilometer scale models have a bias that they make too few big anvils and rain too much and stuff like that. So you could just try to tune away that bias by changing your ice fall speed. So there you go. You're using pattern information to change a physical parameter. That'd be the traditional. That's the traditional approach, I suppose. Yeah.
Yeah. Okay. Yeah. Thank you.
Yeah.
Brian,
Hi, Abhi.
Abhilash.
Yeah.
Actually, you presented the topic in a philosophical way. You turn to be of course, you are a philosopher, PhD,
Yeah.
but you presented the entire problem in a in the perspective of evolutionary theory, but it is slightly disconnected from the I mean, say the predictability kind of the problem. How we will, yeah, that is the disconnect I would see from your presentation. Otherwise, the complex things like the Precambrian life form explosion and the starting from the 3.8 billion years back from a single cell bacteria all the way the spontaneous evolution of that. Maybe the time scale is different, but you are talking about a micro scale or time scale, and that is another thing. But we really enjoyed the perspective in which you presented the much not understood problem of convection, like its complexities. Thank you very much.
Thanks for the opportunity to.
Thank you, Brian. And I found it a very fantastic talk from the basics to the application right now. And it is kind of an evolutionary kind of way you have presented and linking to biology and the systems and I have a couple of questions to you. You mentioned in your talk that the boundary layer schemes are important. And you also mentioned the importance of shear. You have presented actually it can indeed increase the shear at some point, can indeed make more rain. That you indeed was one of the inference. And see, in the monsoons, we have a significant shear, a low level and upper level shear.
Yeah.
So, in that perspective, what is your thinking? Well, actually, we do get a lot of rain, not only due to the shear, maybe also due to the moisture that is coming in with the. So there is more moisture and convergence. Or what do you think about is it in this perspective? Actually, does the game theory work, or means just to, just to there is a transport that is happening, right? Yeah, I saw that you are indeed relating it with the cloud patterns, and yeah, I would like to hear from you on this. Thank you.
Yeah, well, the monsoon, as you say, is characterized really by such strong shear, and that it almost the diurnal cycle, this daily succession game, is a little muted, I think, from the bit I've studied, and I haven't stared very much at the diurnal cycle over South Asia, but it's not, I think it's not like South America where those things are bubbling up freely in that way at all. And the first time I was in India was celebrating the monsoon, and that was right after CloudSat had launched, and I took all the CloudSat objects from the monsoon, and there was day passes and night passes, and I was surprised. It just surprised me at the time how stratiform all the monsoon region cloud objects were blobs. It's not cells, and it's not very cellular, right? And of course in Kerala, the rain is drifting down from really orographic uplift and things. So yeah, the monsoon is just its own beast, I think. It's really synoptic and planetary phenomenon. So I hardly know. We don't get the succession games, so then it's harder to interpret cause and effect, I guess. Yeah.
It is I don't know, it may probably a succession of several events, embedded events. So how even satellite information may be little insufficient to capture that, right?
Yeah, well, it's better than nothing. The satellites are better than no satellites.
Yeah.
Well, all right. I'm looking forward to Dr. Rajiv here, so I suppose I'll.
Yeah. Thank you.
Yeah, thank you.
there is no other questions. Thank you, Professor Mates. That was a very, very interesting session. So now we welcome Dr. K. Rajiv, former Director of SPL BSSC, to deliver the thematic talk. A pioneer in atmospheric sciences, Dr. Rajiv has contributed significantly to aerosol cloud radiation interactions, remote sensing, and boundary layer processes. Through his role at BSSC and participation in national and international research, Dr. Rajiv has made a significant contribution to atmospheric and space science research. Now, today, he will talk on tropical clouds, distribution, energetics, and feedback effects. So, the podium is yours.
Thank you. Can you just put it on? Yeah. Whole thing. CUSAT. Repeat it. Morning, all of you. I hope I'm audible. Yes. The presentation is visible to the online participants. Firstly, thank you, Brian, for the philosophical approach and coming down to the realistic things and the actual problems that we have to do in near future, which is very important. I will go to a slightly different scale, and it will be based on observations with satellites, rather on a global scale, and not on a mesoscale system, but rather on a larger scale system. Basically, what I would like to deal with is the distribution analytics and the potential feedback mechanisms associated. Since there are large number of students, I request the experts to excuse me a little bit because I want to bring in certain importance of the water cycle and then come to the real issue. But I will quickly run through that. First thing is, clouds, when we study, it is not just starting now or a few centuries before. It's actually thousands of years before. We have records of the cloud physics done in a different way, from Kalidasa to P.B. Shelley. I haven't seen a poem, a literature, which is better than what P.B. Shelley has done in terms of evolution of a system, transitions, and destruction. I recommend you to read this poem, especially the cloud. It's an amazing thing and worth spending. And you will get a very good idea about how clouds are formed, how clouds are destroyed. And no word can be taken out from that to that extent. Actually, water has a very freaking nature. And it is very important for the climate of Earth. Mainly, it can exist in all three phases, which is very important for the transfer of energy. It can exist in vapor form and in liquid form, even at below 0 degrees centigrade, superfluid form, which makes it very catastrophic when evolution of the system takes place between the, around 5 to 8 kilometers. And you can have explosive condensation when you have supercooled water and, say, an aircraft enters into that. And that is a real nightmare for a pilot. So they avoid these kind of systems. And water is the most abundant and most variable trace constituent from nearly very low value up to around 4% of the total partial pressure that it can accept. And what is most important is it itself has a greenhouse effect, but the greenhouse effect gets substantially amplified in the presence of water, effect of other things also. For example, carbon dioxide greenhouse effect, it gets amplified when you have water, because it gives more opportunity for longer radiation to be trapped or interacted with. And it is the largest contributor for feedback and forcing and the largest source of uncertainty in modeling. That's why we are discussing it here. From all scales, right across micro scale to the planetary scale. And what is most important from another point of view, especially climate change, is variation of water density with temperature. You stop warming today, ocean will rise for another century, another maybe million years. That's kind of impact that it has. And water is the largest flowing material in the biosphere through the hydrological cycle. And this is the complexity. It cannot be described in one slide, in 1 minute. All what it matters is everything is linked and connected through direct and feedback. A typical example is humidity controls cloud, but you see the way in which it is coming. It controls the temperature, it controls condensation, and condensation in turn controls the clouds, and clouds in turn get affected by radiation, and then it goes. All these processes have to be embedded in model if you truly want to represent it. That makes the models much more complicated. Now, to enable the models to do, it is very important that we need to have observations, and observations interpreted properly. You have systems where, unless you interpret it properly, you can be completely wrong. I'll give a few examples also. And if you look at the energy that is stored in water in the atmosphere, just consider 1 gram of water, how much energy it stores when it is converted to water vapor. You have the latent heat of vaporization. It is of the order of 22 to 58 kilojoule per kilogram of water. And that all happens because of the phase transition. Then if you look at the hydrological cycle, you have huge water reserves for the earth. You have the ocean substantially larger, and but at the same time, when you come to the atmosphere, this total stored atmospheric water vapor content is substantially smaller. It is only around 12.7 kilometer cube compared to the value which you are here. All these values are written in kilometer cube. That is a unit that is coming up here. And the evaporation, ocean evaporation or land evaporation goes into the atmosphere and then comes through precipitation for ocean and for the land. The actual storage in the atmosphere as water vapor is very, very small. And that makes all the differences in terms of our cloud systems. And to form a cloud, there is large number of processes. Each one of these things are research topics, which you can select. And in fact, these are the areas in which now advanced research is being done. From the condensation of a few molecules, which is possible or not, to a large number of molecules coming together to make a sizable droplet for condensation to occur. If you have a few molecules coming in the atmosphere, they do condense continuously, they do get evaporated continuously because vapor pressure required, saturation vapor pressure is not sufficient. The pressure required for that is very, very large. So what you require is a condensation nuclei, which offer a surface area, surface tension forces get reduced. It will be easy for a droplet to grow, and that is aerosols. And when you have a few of them together, coagulate them, and then make it to sufficient size to form a cloud droplet of the order of, say, 10 or 20 micrometers. Let me tell you, this is cloud droplet. It's not precipitation droplet. It is not precipitated because water will be able, this will be able to suspend in the air. That's why we call it as, the aerosol, and then cloud transition taking place. It has to grow much bigger to form precipitation. of the order of maybe 100 micrometer or more than that, then only it will fall. Below which, of the order of 10 or 20 micrometer, it will be all suspended while you are going to see them. And aerosols can affect these systems substantially. For example, the precipitation efficiency can be lowered if you put large number of aerosols into the system. Clouds will be more reflecting if you put more number of aerosols in the system. That is what is called the indirect effect of aerosols, and is one of the most challenging problems in climate change today. Uncertainty factor coming is through the indirect effect of the aerosols into the cloud system, by which the cloud albedo will be enhanced and the lifetime will be enhanced, the precipitation efficiency will be coming down. It's all coming from simple me theory, that you have a large number of aerosols put together, droplet size decreases, radiation will be backscattered more, cloud will be appearing more white. Albedo of the earth will increase. Reduce the surface radiation feeding back to the cloud system. If you look at the total energetics of the Earth atmosphere system, this figure from Trenworth is one of the most classical figures as I have seen. The total energy, if you take 100 units as the total energy that is coming in, taking Earth as a single ensemble, limiting the latitude variation, temporal variation, you have a long-term average of the full global system. So if you assume 100 units is coming in, the solar constant, and then you can make the variation that is actually coming out to be diagonally varying. Diagonal average will be of the order of 341 watt per meter square. Instead of that, you take as 100. There's an imbalance in radiation between the surface and the atmosphere. There is an excess radiation that is at the atmosphere. There's a deficit of radiation at the atmosphere. Excess of the radiation at the surface and deficit in the atmosphere. That has to be balanced. That energy has to be balanced. So there has to be transfer of energy from the surface to the atmosphere, not through radiation, but through mechanical processes. That is the cloud process. That's why you have the cloud systems formed. Otherwise, cloud system would not have been formed. So how much is that? Of the order of 29, if you take 100 as the solar radiation that is coming in, equivalent energy if you take in terms of the transfer, almost 29 is the deficit in the atmosphere and 29 is the excess. Out of that, around 24 is transferred to cloud processes. Only 5 is transferred to sensor-mediated flows. That is hard body to through evaluation. So this makes all the difference in cloud formation and its role in atmospheric analytics. This is what we have just seen from Brian's. This is yesterday's cloud picture from INSAT 3D. But why I wanted to show that is because of another aspect rather than the dynamics of the cloud. But you see the first picture on the left side is a thermal infrared radiation imager that is at around 11 micrometer. And on the right side is the water vapor band that is at around 6.7. The difference, for the same system, you see how much difference you see here. And the advantage of this is where your expertise in making observations and interpretations come up. You can have the Earth surface seen here in the thermal infrared. You will never see it in the water vapor band because even trace amount of water vapor can create saturation. You'll be able to get up to maybe mid-troposphere. You will not be able to communicate through water vapor band. Now what you are seeing here as a hazy picture is actually region of highly humid region. It can also be semi-transparent cirrus. It can be thin cirrus clouds. It may not be very convective, which the thermal infrared will be able to detect. Actually, it is not able to detect. So the thermal infrared will not be able to detect subvisual kind of clouds or very thin cirrus clouds. Because radiation from the surface will be penetrating through. So you need to have a proper understanding on what are the processes that are happening for the radiance that is observed by a system. And that becomes very important. Unless you make it very clear, then your interpretations can be going wrong. And of course, the vastness of the scale sizes from very small systems of the order of kilometers to hundreds of kilometers systems that the cloud systems that are getting formed. If you look at the global distribution of clouds, you already know. This is again for the sake of the students. You have the meridional system that is coming up, that is the Hartley cell, Carroll cell, and Polar cell. And you have the equatorial circulation, that is water circulation. This is already known, but what is most important here is a slightly different one. And that is what I would like to emphasize. You have the, the deep convective systems, and you can have long-range transport of surface. I will say either transport of surface itself or transport of moisture to larger domains through the outflow, which in turn can form in situ formation of cells. That needs to be understood properly. And in fact, most of them will be in subvisual form when it is getting transported far off distances. And as you come to the middle latitude, you see the type of scale systems that are changing. You have the deep convection, that is the deepest convection sitting here. It can go up to the cold point tropopause and affect the tropopause temperatures. Oh. The scale is not screen share. Where is the total mark? So when we close it and then you can. അതോടെ വരുന്നുണ്ടോ? അത് സ്റ്റോപ്പ് ചെയ്തിട്ട് അധികം അല്ല ഇത് അതോടെ വരും റൈറ്റ് സൈഡിലൂടെ വരില്ലേ അത്? Sorry for the coming back. I think we'll continue with yeah. Yeah. So this is what we were discussing about the scale size of the clouds as you move from with the latitude. Oh, it's not coming there.
next slide.
Okay. Yeah. Sorry, a little bit confusion. What I wanted to discuss here is the scale size of the clouds as you move from the equatorial region, that is IPCC region, to the high latitudes, where you have the deepest convection that is sitting here. This generates host of processes again in terms of dynamics of the tropical crust layer, pumping of the water vapor into the stratosphere, which in turn control the chemistry of the stratosphere. There's huge changes that can take place through the brewer loops and Dobson circulation. As you move to the higher latitudes, what will happen is you will have, I think the cursor is not there now. Okay, no problem. Okay, sure. So as you move to the higher latitudes, it becomes shallow convection, especially the mid latitudes. In turn, actually, the water circulation, when you take, you have the deepest convection again taking place in the Western Pacific, East Equatorial Indian Ocean, the warm pool region, where it can extend even up to the lower stratosphere, upper troposphere, lower stratosphere, pumping in. And this is the global mean picture that is derived from CloudSat and Calypso. Around 15 years of image data provided outstanding results that has come up. And in fact, most of our understanding has come from the image data. That is over 50 years of data access now as there too. But there's a problem. Problem is it cannot profile through the cloud system. You cannot have a vertical profile. You cannot have a three-dimensional structure of the cloud systems from the image data. You can have high altitude, low altitude, middle altitude, all those kinds of classifications can be there. To an extent, you have an inference about the vertical development, but they are all inferences. You don't have a direct observation. The direct observation comes from CloudSat data, that is a radar in space, or a LiDAR. Because radar, they'll be they cannot be sensitive to very small cloud water content, means very little optical depth, like submillimeter. If you want to have a total system map, you need to have both visible and radar observations. So that radar will be through the thick clouds. LiDAR will be seeing the thinner clouds. So a combination of them will give you the total picture. This is something which the consolidated picture of the LiDAR and radar data put together and the global mean. And you can see on the top right, you can see that this is the deepest connection, that is ITCC, and this is the actual vertical structure. And when you go on either side, you have the descending limb where absolutely no clouds in the middle troposphere, and all the clouds are actually in the lowermost region. All right, here. And again, of course, when you go to the higher latitude, that I'm not going to focus on. What's also more important is you have large amount of cirrus clouds. That is why in the upper troposphere, you will find that the frequency of occurrence of cloud is very high. The cursor, I'm not going to point to cursor. That's fine. That's okay. You can leave it. Otherwise, it will be more taking more time. Okay. So this is a very important problem. Again, you have large amount of cirrus in the atmosphere because of two factors. One is they are continuously produced, of course. The residence time is very high. Unlike the other cloud systems, when you go out and see an mesosphere conductor system, the cloud system may be there for a long time. But the cloud is not there for a long time. Cloud is continuously evolving. If you play like a movie, it will be something like, quickly transforming and then again it will be formed and again dissipated. Whereas cirrus is not like that. Cirrus can have longer lifetimes, out of a few hours, and at times it can exceed even a decade. Of that will come to. So the feedback comes through the IR radiative forcing, shortwave radiative forcing, and changes in any aspect of the cloud. If you change from ice cloud, water cloud to ice cloud, or the other way, when it is transforming, you actually feed back to the system. Cloud altitude change, cloud particle size, shape, or lifetimes, all these things will affect the degree to which clouds warm or cool the earth. And all of these feedback mechanisms, if you put together, it's mind-blowing. And that is one of the problems that is the most challenging problems in the advancement of cloud modeling and associated processes. This is the mean picture of the global mean distribution obtained from image data and the corresponding precipitation. The bottom one shows the image observation of the total mean cloud occurrence from ACCP, which is a combination of climate quality data for all the satellites put together for long record. I took it from Ashwati now. So you can see the cloud occurrences. You can see that, the ITCC region where you have the maximum cloudiness all over the globe. This is a global mean picture, annual mean, long term. And you can also see that it is totally asymmetric. It is not symmetric with respect to, it doesn't appear as a single map. And that is why you have the Walker cell. The Walker cell coming, the Indonesian region and Eastern Equatorial Indian Ocean, Western Pacific. You have it on Africa, Central Africa, near the Congo Basin, and or the Amazon region. These are the regions where you have large amount of clouds. You will also find large amount of cloudiness at the subtropical region. For example, South America, Southeast Pacific, Southeast Atlantic, and Northeast Pacific. They are actually not developing clouds. They are actually marine thickness cloud. But then the rock thickness is as high as most of the clouds which you see here. Even the water content can be quite high. The water system is very, very high that they are highly reflecting. In fact, the radiative forcing coming from that is almost comparable to you have a deep convective system. And that can cool the surface substantially, but then they will not develop into more than maybe 2 kilometers or 3 kilometers. And their precipitation efficiency becomes very low. You can see that all those regions are having very less precipitation. But then cloudiness, if you look at, they are among the largest. And this is the actual classification of clouds into high, low, and middle level clouds based on radar and LiDAR observations put together. Because in an image observation, when you have a high level cloud, actually the middle level cloud is masked or low level cloud is masked. So what you get is an inference, not a very direct observation. Whereas when you are putting the cloud set and calypso together, you get a picture which is actually giving you the low, middle, and high level clouds. Why it is put together is because have a comparison with what the ISCCT or the other, satellite data, image data is giving. So it is almost comparable. It is not that there's a substantial difference. Of course, there will be some small magnitudes, especially in terms of the low-level cloud occurrence below the deep convective systems. But otherwise, there's no major differences that will be given. What is most important here is the deep convective systems that is shown on the rightmost side. Where you can see that the deepest convective systems are the red globes are coming. The y-axis is actually the panels are for different seasons. One is for the top is for December, January, February, that is been and northern winter, March, April, May, June, July, August, and September, November. What you will find is large amount of deep convective clouds occurring. Of the order of 20% is the deep cloud occurrence frequency over the Amazon during the the southern summer, that is northern winter, which is quite large, very large. And in fact, it is comparable to the East Equatorial Indian Ocean, Western Pacific. You can also see June, July, August over the head bay of Bengal. You see that red patch there. That is among the deepest in the world when you come to the in terms of altitude and in terms of impact. It's quite large system, and its impact is very huge. If you look at the radiative impact, that is a direct radiative impact that is coming from the reflection or emission at the top of atmosphere. You will get the short wave cooling. That is, when a cloud is there, it is going to lose the radiation from the Earth, so that the Earth's surface will be cooled. That's why we say cooling. Actually, top of atmosphere will be gaining. The magnitude is of the order of minus 47 1 kilometer square. When it comes to longer, it has longer emits, and that can be trapping. And the radiation that is going to space will be reduced when you have cloud, because cloud temperature is lower, surface temperature is higher. So what is going out will be lower. So it will cause a net warming effect here. And if you take the net effect, that is sum of these two, taking into account the directions, what you are getting is a net cooling. But this net cooling, this is actually cheating. This net cooling is a global mean thing. You take day and night, you don't have short wave radiation coming. So you have only long wave radiation, that's always warming. And in the daytime, you have substantial amount of short wave radiation coming. So it will be much annulling the long radii effect. So there's a huge diagonal variation in radiation balance because of the cloud itself. That itself will drive another process. So it's not a very straightforward thing as you see in a picture like this. It's much more complicated. This is something which Minu has done for the Indian region. The cloud distribution, especially in terms of the frequency of occurrence of clouds from AVHR for a longer period, as part of the PhD work. One of the things which, again, this is an image data, but we have to cut through this. And that is why I'm stressing on why the radar data is essential. Just look at this. This is the June-July August pattern that you see here. You have Bay of Bengal, very deep convective, because the temperature is very low. So we know that it is very deep convective. And this is the kind of pattern that exists there. And if I cut it through with the radar, so the panel will be, I'm taking different longitudes here and segmenting it as a latitude variation. You see here. And you see several features which are not seen, which are not evident in the image data at all. For example, you just look at here, at 80 to 90 degrees, the third panel from bottom, you have a blue region that is sitting in the middle, right in the monsoon region. That is called the pool of inhibited cloudiness that was found from the CloudSat data, because up to around 7 kilometers, around 1 million kilometers square area, absolutely no clouds. But the image data will not reproduce that exactly. Of course, there will be a deficit in cloudiness if you look. Actually, that is cirrus clouds. They are not disconnected clouds, they are not even connected clouds. And that information will come only from the radar data. So there are things which are masked by the upper level clouds, which if you want to see, you have to profile it through. Then you will be able to study this. And one of the most important things is in that region, you can see that the Bay of Bengal region, which is very deep in deep, it goes up to around 16, 17 kilometers deep. It can, very significant amount. And the fraction of that can cross the Copeland River that we will come to. And you have at the other side, you have the equatorial trough toward the south. Then you have the pool of inhibited cloudiness coming in. And the cirrus flow across that will be actually telling you that enough amount of cloud is there. But so your image will not be able to see that. That's what I wanted to tell you. And long-range transport of cirrus. You see the deep convection, and you can see the anvils that are spreading. It is not just the anvils that are spreading. Actually, it becomes thinner, and finally it becomes extremely smaller. It can actually, if you look at the trends, it can go back to the descending region of the atmosphere. And this is what when you composite, and then the effect of particle easterly jet stream in transporting the deep convective from the deep convective cloud to the western part. That is the arrow that is indicated. And this is what Anish has investigated in detail about the pool of inhibited cloudiness. And the region where you can see that there's a large gap of cloudiness that are sitting here. And it is not well reproduced in the vertical velocities. Of course, vertical velocity shows a small deficit, but then it is still convective. But the fact is, it is not. It is not a part. So if you want to, if the have the other observations like scatterometer. If you look at the scatterometer shows that the surface wind is diverging, which means there has to be descending from the upper velocity. So if you put all these puzzles together, you will be able to formulate a new system that is, embedded in the large scale system. And why it is supported? It's supported because you have on either side of the wall, you have the latent heating that is liberated substantially. That will heat the atmosphere, which in turn will give rise to another circulation of this sort. This is what we propose. A mini circulation that can be embedded within this. And in fact, this was also observed that when the pool of inhibited cloudiness is strengthening, it also strengthens the deep convection that is happening in the Bay of Bengal through a feedback. The second aspect which I am coming to is in terms of SST cloudiness relationship. SST convection relationship. Conventionally, we have the total evaporation that has to take place in the surface. And the surface SST is larger, then obviously there will be larger evaporation. So there will be a direct linkage between SST and the sea surface temperature and the cloud convection. So historically, people have studied this. Actually, there is a then Gadgil and Sika, Rajendran, Sabin Joseph, and Min. All these people, and several other publications are also there in this. This is very important publication in terms of concept. You have an enhancement in the cloud occurrence taking place after around 26 degrees centigrade. It attains a peak somewhere around 29 degrees centigrade. And then there's a reduction in cloudiness as the ocean warms. That's a very conspicuous thing that we have to address. Is it really there or what is the mechanism for that? And if that, because another matter as far as the climate of the atmosphere system is concerned, it is not going to be a very simple thing. It regulates even the climate of the atmosphere system through thermostat effects and things like that. Now, this is what the imager has shown. This study has been done with years of data from image observations globally. And this is what the CloudSat or the radar observation show. The radar observation show what is the altitude, AX is altitude, X-axis is SST. And if you look at, you can find that there is an enhancement in convection only up to around 27 degrees centigrade, not 26 or 26.5. In fact, it comes even not at 27, 27.5 kind of thing. So almost a degree change in terms of the convection triggering. Then why the imager was showing a wrong thing? It was not showing a wrong thing, but rather it is an interpretation problem. Because you have a deep convection and the deep convection region also will have an outflow. The outflow region, it can extend to very large distances. There the SST is lower. So all what we did there is an SST relation with the cloudiness. And that is the information that is available with that. If you really find that, this is the kind of figure that it comes. And there's one more thing that comes here. If you segregate into different altitudes, actually the low-level altitude clouds intensity comes down as SST increases because now clouds are getting more ventilated upward. At the same time, the high altitude clouds get enhanced. Of course, that is expected because of the deep convection. Okay. And which I told that the conspicuous thing has come, it actually because of the outflow. This is exactly a relationship between SST and altitude, just in terms of, you can see that it is, even out there at the region where you have intense cloudiness, SST slightly decreases. Actually, it is not the problem with intense cloudiness, but rather the cirrus outflow, which we interpret as clouds, otherwise, in the imager observations. This leads to another problem because you have a reduction in cloudiness that happens after around 29.5 or 30 degrees centigrade. Cloudiness starts decreasing. Why? It's an important problem because, especially in a climate change scenario, this becomes all the more important. And in fact, you can go through the literature. This is a research area, iris effect. That's one thermostatic effect. They are all linked processes, but they're not exactly the same processes. The CloudSat observation doesn't show that it just decreases the way in which it was otherwise coming if you take only the deep clouds. But if you cirrus clouds and things like that, of course, you have a reduction. It is also very clear that you have the Arabian Sea warm pole in May over the Indian region where the SST becomes more than 30 degrees centigrade. Much of the region is cloud free. This is what the left side figure shows the main imager. You have the SST contours. 30-degree contour is not at all having much cloudiness. It is of the order of maybe 30%, 40% cloudiness. Whereas 30 degrees centigrade SST, when you come to June, July, August, you have substantial amount of cloudiness. So these are the things which we have to have proper understanding and interpretation. I'm not coming to a conclusion here, but rather these are the areas where people have to focus on to bring in new understanding. And of course, it is simply because the SST is not the one which is regulating. There is SST is one factor. SST gradient has to do with the dynamics because such gradient will be here. You have the surface wind divergence or convergence will further enhance the moisture going up. Convective available potential energy for the atmosphere has to be sufficiently larger. Lower tropospheric stability and instability has to be more for convection to develop. And you should have vertical winds beyond 0 degree isotherm. All these parameters, when you put together, you will get the correct relationship. But then it is not just one end problem. And all these problems are actually, the parameters are also linked. It is not that they are isolated. SST is not isolated from SST gradient. They are not linked, but doesn't mean that a most warming region can be having low SST gradient. This relationship which you can see with respect to the surface wind divergence, for example, or vertical wind. I will not go into the details here. The third aspect that we should look at is the deep convection that happens and the extent of deep convection when it is going to the stratosphere. Well in the equatorial region, which can be considered as a pipe through which stratosphere exchange takes place, significant amount of deep convection can pump into the moisture or clouds even to the low stratosphere. Clouds do penetrate 4.4 past. I'll come to that. So this is one area where we have to address, especially when it comes to the cloud effect in the stratosphere. This is the map of the cloudiness where the clouds are crossing the cold point to pass. We don't usually, most of the clouds doesn't cross the cold point to pass. But this image shows based on CloudSat observations the frequency of occurrence of clouds beyond the cold point to pass. Right, and it can be quite high. It can be of order of 20% in December, January, February over the Western Pacific, or the Bay of Bengal during June, July, August, September. And it's quite high. You may think that it is very high, but I'll come to that very soon. You know, if okay, sorry, just let me interpret it here itself. This is penetrates, but how much is the extent of penetration? The penetration extent can be of the order of 1 kilometer to maximum 1.5 kilometer, and in very rarest cases we have seen up to 3 kilometers, but that is extremely rare. It is not that it goes far into the stratosphere. It just crosses the cold point to focus, but then the whole process becomes completely different because there is more stability there. Lifetime can be much larger. And suppose you have large number of big clouds, which are big droplets which are going up. It will dehydrate the system because what happens is it will also take out the moisture that is available there and it will be falling down because atmosphere will not be able to support it for suspension. Whereas these tiny droplets, they will go in, they will get evaporated, they will add moisture to the stratosphere. So it is not that, once you have cold point crossing, it will simply moisten the stratosphere. It need not necessarily moisten the stratosphere. It can do either of us, which means you have to look at the microphysics of the cloud. Then what is the cloud droplet size distribution, which is crossing? It becomes very broad. Another aspect which when you look at in terms of the image data with respect to the radar data, we have already told about the water circulation. This is easter circulation. The average of the cloudiness in the tropical region, which is 30 degrees south to 90 degrees north, if you average it put together in the formal direction, entire formal direction, entire tropics, you will get 3 ascending winds. Of course, we know all those things. What is that? You have the biggest ascending wind in the world, Indonesian sector, East Indian Ocean, and the Africa, the Congo, and the Amazon region. But if you very carefully look at the Western Pacific, East Indian Ocean is not a single thing, like conventionally what we believe from the major data. There's a very clear split that happens, and the split is having an annual oscillation. That's what you can see at the bottom. September, October, November, they are seen as 2 separate vertical bands, with a distinct decrease in the cloudiness in between, especially that takes place between around 120 to 130 degree longitude. It can be of the order of 110 to 140 hours, depends on the season which you are looking at. So they are not a single largest ascending limb over the Arabian Sea, the Western Pacific one code, but rather there are splits. There are reasons that we found out, especially the Micronesian islands play a major role in regulating this. This is one of the observations that comes up from the radar observation when you put together instead of image. The second aspect is in terms of the WITCC. Usually we think that WITCC is a very rare phenomenon. It happens only in the Western, where the Eastern Pacific during March till May. This, of course, its occurrence is quite high there. But it is not so. It is much more frequent if you look at the CloudSat data, because again, I'm telling you, the image observations where the cirrus was masking the split in the WITCC that otherwise would have been seen. It doesn't mean that WITCC is omnipresent, no. But then the frequency of occurrence of WITCC is much larger than what is understood so far. This is an example of that. You can have the Southern Pacific, you can have the Eastern Pacific, you can have the Western Atlantic, and over the Pacific, from around 140 degrees east to up to around the Eastern Pacific. South Pacific to Eastern Pacific, it is present almost through in the April, May. And the right side figure shows how much is the collaborative heating that is coming from, the right heating that is taking place. And to what extent this double ITC structure is seen in the raw data, that is the rightmost. And you can see that over the Western Atlantic, it is not seen at all. Because it is again not a major issue. It will be resolved provided you may be running a very high resolution thing. But here the resolution may not be sufficiently high to resolve it because the ITCCs are very, very finely, very, very close by. Coming to the energetics, the clouds, you can see the focus on the right side. You will find that there is substantial amount of heating that takes place because the latent heating that is coming from the cloud. It can be of the order of 0.1, 0.2 Kelvin per hour. Another very interesting study that has come out from the cloud observations from radar is, you have the nighttime versus the daytime. If you see, we always think that you have preferential region over the land. You have the afternoon convection, and then the you have the early morning convection for the ocean. But immaterial of all those aspects, if you look at the topmost region, you take the difference between day and the night, whether it is ocean, whether it is land. You have the daytime larger and nighttime lower. That appear as the topmost, that blue band that you see appear at the topmost. This actually comes from the short-wave heating of the cloud at the top, which in turn will heat it, and it will have a radiatively driven convection. It's already proposed, it's already known. But then this shows an evidence for the radiatively driven convection. What is shown on the right side, the XY graph, is the cloud size distribution, height, depth distribution, thickness distribution. You'll find that during the daytime, you have an enhancement in the towards the tail end. Of course, it is in log scale. You have an enhancement in the tail end, and that enhancement is very weak in the night and very high prominent in the day. This further substantiates the radiatively driven convection that is coming from the short-wave absorption of the cloud top. Metrotropics provided us an opportunity to evaluate the diurnal variation of the cloud-relative impact over the entire tropics, because it covers all local times over a period. It is not that in a single day. In a single day, it may be of the order of 3 to 7 passes over a specific region. But if you combine for around 50 days, that is 50 days, that is the satellite orbit cycle, you will be able to derive the diurnal variation. And that is what is shown on the left side is the longer radiative forcing for different times, local times over the entire globe. And on the right side is the combination of the net cloud radiative forcing that is coming from the short-wave background. I told you that the clouds can penetrate the 4.2 pulse. To what extent? This graph shows how much is the extent to which the frequency of occurrence of clouds which are crossing the 4.2 pulse, or which are actually reaching up to the cloud top, up to the base of the the tropical tropopause layer. So when you classify all these things, you will find that on the right side, you will find that there is the volume of the extent to which it is crossing over. The 4.2 pulse is substantially higher. The amount mainly comes from the deep convective cloud rather than from the cirrus clouds that are formed in situ there. Their number is quite small. Those which are formed above the 4.2 pulse. The number is there, but then the number is very, very small. The other thing comes from the convection that is going from the troposphere and then entering into the stratosphere. And of course, it has its own structure because the depth, the penetration will take place maximum over the ascending limits of the water cell. And this pumps up the moisture into the stratosphere. And then you have the tape recorder effect that comes where systematically you have an annual cycle of pumping up the moisture going up to the 30 hectopascal level or even beyond, where it of course will have a role in chemistry of the stratosphere. So you see how it is linked from the processes that are here and then getting into the chemistry aspect. This is already investigated from satellite data. Of course, it is already done from the Indian side by Sunil et al. Based on cryogenic force point hygrometer launchings, regular, systematic for multiple years. One more aspect which I would like to cover to show the total gamut of the gain again is the effect of galactic cosmic rays in cloud formation. You have the cosmic rays that get modulated by the solar wind and the phase of the solar cycle. Galactic cosmic rays can ionize the CCNs. CCN, once it is ionized, precipitation efficiency, the droplet formation efficiency is very large. It can grow rapidly compared to the non-ionized things, which in turn will modulate your low-level clouds, which in turn will have a change in the surface energy budget that is coming from the clouds. This is one idea which is, these are all not very recent. It is actually 2000 onwards, people are seriously working on these aspects, but when still these are all unresolved issues because you need to have any season it will occur. All what it matters is how much is the galactic cosmic ray coming, getting modulated by the solar, because the phase of the solar wind can actually modulate because of the interactions between the dark particles, which in turn will have a chain of effects, which from the tropospheric ionization to the CCN formation to the changes in the surface and then the hydrological cycle. If you look at the magnitude is minuscule. Then why should we look for that? It is not very important for weather. May not be very important for weather. It is very important for climate. The reason being the global climate warming, or the in terms of the relative force, it is of the order of 3 watt per meter square. Approximately, it may be slightly larger. In terms of the solar cycle variability, this is almost 1.2 to 1.5 watt per meter square. So there is a comparison between them in terms of climate when you are putting it. This probably I will skip. And of course, when why I put this is because of another reason. If you look at the lightning, which is another aspect which we have to look at from this, thunderstorms and lightning, thunderstorm from the weather and lightning as far as we are concerned for the electricity. And you know that a large amount of these primes and things like that, which in turn can link to the atmosphere and connect to the ionosphere, because the global electrical circuit is connected to the ionosphere through these sprites and the connection that come from the lightning, which becomes a very important part for the ionosphere research and the impact of the I just wanted to put that as a total picture for the students. It is not just these later ones which we showed is not our findings, but rather it will be interesting because I understand that this is a different background people. So I thought it would be better to say there can be a serious role for the deep immunity clouds in the atmospheric electricity, even the current global current systems. In addition, it will also produce worlds, gravity worlds especially, which can be going up into the atmosphere and then trigger also atmospheric features. I will not go into those details. So I thank you very much. Thank you for a little bit disturbances. So I have to go a little bit faster. But I understand everything is connected and everything is linked together. You cannot isolate one from the other. And if you want to connect everything, it becomes chaotic. So you cannot connect. It becomes extremely complicated. Thank you very much for that. And then thank you for inviting me for this. It's an honor.
Thank you, Dr. Rajiv, for the detailed and yes, sir. We welcome a couple of questions from the audience now.
I would like to know the implications of the 2D round hole that has been shown through the satellite images, which is present on the Burma region from the presentations. So what would be the implications of that circulation?
Very important question. So when we are looking at the implication, we have to know how it is formed. It's formed on the surface in divergence. That surface in divergence is actually triggered by the convection that is taking place in the surrounding areas. Larger the convection, there will be, a differential convection coming. It needs a place where immediately to sync rather than going into the large scale thing. Of course, 90% may be going in the large scale, going to the descending limb of faculty. But then a fraction will be immediately sinking in there. So you have now walls surrounding this, where deep convection enhances, it will enhance the descending at the pool of individual clothing. This is what we observe. Actually, there was a subsequent paper by Anish. I did not show it due to lack of time. If you put in terms of the strength of convection that is taking place in the Bay of Bengal versus the pool of individual cloudiness size and the extent, they are linked. It is dynamically driven. But actually, it is like this. When you have a very deeper connection that is taking place, the surface wind divergence will enable, because surface wind divergence will naturally move the air. And that will be moving partly to these regions, which will accelerate the convergence that is taking place in the Bay of Bengal. Similar thing will happen in the south and the west. So it will be something which is not investigated in detail. And models are not able to reproduce this to a large extent. So when you are trying to initialize the data and all those kind of things from clouds, unless you inject the vertical distribution of clouds and heating, I will not be able to do that. I'm not a model. Unless you will not be able to reproduce this. This was done to an extent. There were two groups. I think IITM and Mukherjee, his group tried to do this. He has a presentation. So he tried to do, and then CG tried to do some SPL. So there were few people who are attempting this with success, limited success. So better understanding is coming from the observation, but then it has to be put in the model. But definitely it is affecting the transformer, especially the ascending limbo, the deep connection of the wave. Right. Actually, you have a huge differential heating that is coming. That itself can differential heating, diabetic heating. That itself can trigger. Yeah. Any other? Okay. So I think I don't know whether there's any online. No. Okay. So thank you very much. Thank you, brother.
At this moment, we are privileged to felicitate Dr. Rajiv in recognition of his decades of scientific leadership, mentorship, and service to Indian atmospheric research. His expertise lies in atmospheric science, focusing on areas such as atmospheric aerosols, clouds, radiation transfer, boundary layer physics, atmospheric dynamics, and climate change. He also specializes in satellite and LiDAR remote sensing and inversion methods. Dr. Rajiv obtained his PhD in physics from SPL and University of Dhaka and did his postdoctoral research at the Self Institute of Oceanography, Santiago, USA. He is the national representative post-doc council and member of the research advisory in the society. And now we will have a 10-15 minute break and we'll convene after around 12 break. Thank you.
സാറിന് പെൺഡ്രൈവ് സാറിന് പെൺഡ്രൈവ്
അല്ല സർ അത് തന്നെയാണ് കൺഫ്യൂസിംഗ് ആയിട്ട് തോന്നുന്നു PDF എല്ലാം ഇതറിയില്ല ഡെസ്ക്ടോപ്പിലുണ്ട് ഡെസ്ക്ടോപ്പിൽ ഇട്ടാൽ മതി താഴെ കണ്ടുപിടിക്കാൻ തുണിയൊക്കെ ഡെസ്ക്ടോപ്പിലുണ്ട് ഫോൾഡർ ഒന്നും ഇട്ടില്ലല്ലോ അല്ലേ ഇട്ടിട്ടില്ല ആ ഡെസ്ക്ടോപ്പിലാ ഡെസ്ക്ടോപ്പിലൊരു പുതിയ ഉണ്ടായിരുന്നു പോയിന്റർ നടുക്കല്ലേ അതിപ്പോ സേവ് ചെയ്തിട്ടില്ല അല്ലേ അതന്നെ ഓക്കെ സാർ കൺവീനർ തന്നെയല്ലേ ആ അതിന്റെ
സൂമിലെ പ്രസന്റേഷൻ സ്റ്റാർട്ട് ചെയ്ത് വെച്ചാൽ
സ്മിതേച്ചോട് പറഞ്ഞു
അല്ല നമ്മളെ സ്ക്രീൻ ഷെയർ ചെയ്ത് വെച്ചേക്കും ആദ്യം ചേച്ചിയല്ലേ
രണ്ടാളല്ലേ ഉള്ളൂ
വീഡിയോ സ്റ്റാർട്ട് ചെയ്ത് വെച്ചു ഈ ക്യാമറ കണക്ട് ചെയ്യാൻ അരുണെന്തേ അരുണെ വിളിച്ചു
അല്ല
ഈ ക്യാമറ കണക്ട് ചെയ്യാൻ
രാജീവൻ സാറിന്റെ
Yeah, yeah. That's
Hello. Hello, Abhilash. Yeah.
Hope everyone is settled. We now move into our first technical panel on tropical convection and organization of clouds, focusing on a theme that lies at the very heart of tropical meteorology, the structure and organization of convection and cloud systems. In this session, we'll hear from two leading researchers who bring both observational and dynamical perspectives on these processes. Their work highlights the importance of cloud microphysics, convection circulation coupling, and regional specificalities in how we interpret and model monsoon systems. This session will be chaired by a retired professor, Dr. C.A. Babu. Our first talk is by Dr. Ayantika. She is currently working as scientist at Center for Climate Change Research of Indian Institute of Tropical Meteorology. Her research focuses on South Asian monsoon dynamics and variability, extreme precipitating systems and climate change, and Earth system modeling. She has done fundamental research work using atmospheric model simulations and diagnostic analysis of observations, highlighting the critical role of the vertical distribution of latent heat of monsoon convective cloud systems in influencing the summer monsoon circulation. Additionally, Dr. Ayantika has contributed to the development of the IITM ESM, the first climate model from India that participated in CMIP 6. Dr. Ayantika, you can now share your slides and start the talk. You'll have 30 minutes for the presentation.
Okay, thank you. You can see my screen. You can see my screen.
I can see.
Okay. So thank you, and thank you to the organizers for inviting me. So I will be mostly talking about this tropical cloud system and how it interacts with the monsoon circulation. So how it interacts with the large-scale monsoon and how the feedback processes between this convection and circulation happens over our own region, South Asia. So this is the picture here shows the cloud map of yesterday. I think Dr. Rajiv also showed it. So here we can see that the cloud system are organized into a large scale structure across the entire subcontinent from Western India across central to the head Bay of Bengal. And this is very unique to our region where we have this 3,000, 4,000 kilometers large scale organization. And this has a very significant impact on our circulation. So again, reiterating what Dr. Tara, Dr. Rajiv, and Professor Brian said, heavy precipitation over the tropical regions, it mostly occurs from these cloud clusters, which organize into weather systems, which spread across few hundreds of kilometers. And in this paper in Hamada, what they did was they categorized these cloud structures based on the intensity of rain and the size. And we find that this orange here basically is very intense rain occurring from large systems. So we see over our region, especially over the heavy precipitating regions like the North Arabian Sea, Gujarat, Western Maharashtra, as well as the head Bay of Bengal, we see the systems are large and the intensity of rain is very high. And if we look into the cloud top height, we find that there are very tall cloud heights. So it is more than 14 kilometers. Dr. Rajiv was also talking about this. And these cloud clusters, they occur within the envelope of the large-scale circulation. So they are embedded within the ITCZ or the monsoons. So in this paper by Vyasuti et al., what they did was they looked into these cloud structures. This is a snapshot of 27 July from the GPM precipitation. And we see this green and red, they are rates of precipitation. So the precipitation that is coming from these organized cloud structures. And the pink here is the very high humidity region. So these cloud structures are embedded within regions where very high humidity occurs. And these regions are also coincident with the planetary scale circulation, that is the monsoons and the ITCZ. The organization and movement and the characteristics of these cloud structures are dependent on the background flow, on the vertical shear, on the base surface boundary conditions, as well as these cloud structures feed into the system. So there is a feedback process that goes on. Now coming to our own region, the South Asian summer monsoon, this is a classical example of the multi-scale interactive phenomena. We have this weather systems, like we can talk about metropospheric cyclones that occur over the Western India and gives us heavy precipitation. We have the monsoon lows and depressions, which again form over Bay of Bengal, propagate inland. We have the active break cycles, and all this happens in the background of the large-scale circulation. And this organization movement of this system, which is modulated by the large scale, it plays a very important role in the precipitation variability over our region. Now, over the tropics, we know this is just going back to the basics. We know that the tropical precipitating system can be categorized in two different forms of precipitation, that is convective as well as stratiform. Now, what do we mean by convective? They can be identified from the radar echoes by very intense peaks. They usually are the young active region of convection where vertical velocities are very high, where the growth of the particle occurs due to collision coalescence and then riming. And then we have the older part of the less active convection, which we call stratiform. And these are characterized by broad radar echoes. And it is a distinctive signal is the presence of a bright band, that is the melting layer. Here there are more gentler motions. We have the growth of the particle that occurs from vapor diffusion and as the particle comes down from accretion. But these two regions are very distinctively different in the type of latent heating that is generated over that region. And this plays a very important role in modulating the circulation. So from the convective regions, what happens is, so here below you can see that the vertical profile of the convective region has a single metropospheric heating peak, which occurs at about 5 kilometers. But the stratiform region, from that melting level, it has got a heating peak at a much higher level. So at around 400 HP or 8 kilometers, we have the heating peak, which is called the elevated heating. And we have a cooling peak from the evaporative cooling in the below layers. So this generates a very strong vertical heating gradient at the mid-tropospheric level. And this gives a very different signature in the circulation. So this is a plot, a representative plot of the retrieved latent heating. Actually, in the recent years, past 20 years from since TRMM was launched and now GPM, we can get this from the PR precipitation rates, the vertical profiles, we can get this vertical heating profiles over the entire tropical region. So here we have different panels, which shows the lower panel. It shows the surface rain rate. So we can see, since this is the annual mean, we can see the intense precipitation occurring over the equatorial regions. You can see here over the West Pacific and this Indonesian region. And as we go up in the higher up in the height from 2 to 8 kilometers, this is the heating. And we see that where we have intense precipitation, the heating profile shows that it is maximum at 8 kilometers. So basically, these heavy precipitating regions are dominated by stratiform type of rain, and the circulation is modulated by this type of rain. Over our Indian region, this is from work by Bob House. So the top panel is the seasonal mean precipitation over our region. Now, if we partition the seasonal precipitation into convective and stratiform, the left-hand panel is for the convective rain that is happening during the monsoon season, and the right panel shows the stratiform rain that is happening during the monsoon season. So let us concentrate in the lower two panels plots here. So these are the fractions of rain that are contributed by convective and stratiform. So you can see in the left-hand lower panel, the fractions here, this blue color, it shows lower convective rain fraction, whereas this red is a higher rain fraction. So if we see this Himalayan region, the Indus Valley, and as well as the IGP plains, we have higher fraction of convective region, convective precipitation. But over the core monsoon zone, when we have more precipitation, where we have like more precipitation, I mean where we have this active break spells where the monsoon depressions passes through. Also over Gujarat region, we have less convective, and we can see the red percentages, that the higher percentages over this region is contributed by stratiform rain. Also over this northeast region, we have very high stratiform raining systems. So, and this would, the implication of this is, since these two type of precipitation has very different vertical profiles, so across this region, the maximum height of this latent heating profile will vary, and that will significantly impact our monsoon circulation at different space and time scales. So here we are taking a look at the active monsoon period. Now, when we look at the rainfall during active monsoon shown in the left-hand plots here, so this is the composite of rainfall. So the top panel shows the composite of total rainfall. We can see that during an active monsoon, we have rainfall which extends from the Western India. We have intense precipitation over Western India. It extends across Central Bay of Bengal and into the Bay of Bengal. So basically it happens that shows that there is a large scale organization of this system. So it is not one or two mesoscale systems that are occurring. So the entire 3,000, 4,000 kilometer, there are systems which is generated in situ. And we have this entire organized band of clouds. And this is a very representative picture from yesterday, as I showed. So you can see this organized band across this extended region. Yesterday, we had a very active monsoon case wherein we had precipitation from a low pressure in the Chhattisgarh, Jharkhand region. We had precipitation over Gujarat as well as the eastern India. Now, if we take a transect over this Bay of Bengal region or any system over this Western Ghats during this period, so this right-hand side, I have an example of system using the TRMM observations. And we have taken a transect, we have taken the vertical cross-section and looked how the radar echo looks during this active phase. So you can see from these two radar echoes, this intense convective cells are there. And along with that, we have this broad raining area, broad peaks, and a bright band, this occurrence of a bright band you can see, which shows that during this period, the systems are mostly of stratiform type of precipitation. So now to understand how these type of precipitating systems and their differences in associated latent heating. So these regions will have very different vertical profiles of heating, and it will simulate very different convergence and divergence center. So how that works, we used a very simple model. Okay, now just to look at, so this was the precipitation rainfall anomaly. Now what happens is during this period, what is the circulation? So if we look into the circulation, we find that the circulation has a very broad extent. The circulation is also not localized over the Indian subcontinent, but even at the mid-tropospheric level, we have a circulation which extends from the tip of the Arabian Peninsula across Arabian Sea, Indian subcontinent into as far as the South China Sea. So this has a very elongated east-west oriented cyclonic circulation is established over this region during the active monsoon cases. And if we take the relative vorticity over the monsoon trough region, we see that during the active phase, so the dashed line here is the relative vorticity during the mean monsoon, where like mean conditions. But during the active phase, we see a significant deepening of the relative vorticity over this region. And there is a stretching in the vertical also. So to understand this, what we did was we took the rainfall anomaly over the region and we did some idealized experiments. Like we considered that this entire rainfall anomaly is occurring from only convective systems. So what happens to the circulation then? Then slowly in different experiments, we started introducing stratiform type of clouds, which we actually see that is predominant during this active period of monsoon in the region. So we did an experiment with 0, then 30%, 50%, and a very high stratiform 70%. So on the right-hand side, you can see the vertical profiles at a representative location when we do this experiment. So this yellow is basically when we have 0% stratiform in the anomalous rate. So we have a background stratiform already. So that's why we don't see the exactly that heating and cooling over here, because the background already has a distribution of stratiform and convective, the mean condition. But during the active, now we are changing how much of convective systems are generating this convective or stratiform precipitation. So when we look into this profile, we see as we introduce more stratiform type of raining systems into the region, we see that the heating peak gets elevated and we have a stronger heating gradient in the mid-troposphere. So we have a top-heavy heating structure with a very strong heating gradient in the mid-troposphere. So with this, we run a simple model and we see that these are the plots of the mid-level circulation, the circulation and the stream function. So we can see as we go from stratiform, 0% stratiform to 70% stratiform, this elevated heating, it intensifies the mid to upper level circulation. And it gives us a large scale character also. So basically this vertical distribution of heating that is within this type of different cloud clusters, it plays a very important role in defining what type of circulation we will have, how deep the circulation will be, how large will be the spatial extent of the circulation. So the proportion of the cloud systems, how the cloud systems are changing also with climate change is very important for our region and our monsoon circulation. So keeping this in mind, we would take a look at a some of the heavy rainfall and deep convective events over our region. Now, we know that with climate change, we are having more of intense rain episodes and deep convection floods over the region. So here what we have tried to do is we have tried to take the heavy rainfall over the Indian region, and we have looked into the frequency of the heavy rainfall. So it is not only extreme, it is heavy, so that we can get the organized convective systems. So it is just 95th percentile, and it is raining over the larger area, not localized cells or over single grids. So we can see that the slope of this, the change of this heavy rainfall frequency trend, shows that the heavy rainfall, heavy precipitating systems are increasing over the Western India while it is decreasing over the Eastern India. And that is similar to what we see in the deep convection activity. So if we count the deep convective grid from organized convective system, we find that these type of systems are increasing over Western India. So what we did was we wanted to look what is happening over the years. And so we plotted the mean monsoon rainfall from the start of the century till now. And so these green bars here are the seasonal mean rainfall over Western India. And very interestingly, we find that the 2019 monsoon shows the highest seasonal rain in over the century. And also we know that 2019 monsoon was a flood year over entire India, and it was flood after 1994. So we plotted the DMI also, and we found that it is coincident with a very strong DMI. So the SST gradients also play a role in the development of these convective systems. And when we counted the heavy rainfall count over the Western India, we find again 2019 stands out. So now this is just to show what happened in 2019. And we can see that this is a subdivisional map by IMD, and we can see that 2019 we had extensive rainfall intensification over the Western Indian region, particularly the state of Gujarat received 166% of the rainfall. So it was heavy flooding over Western Maharashtra, Gujarat, West Coast, across West Coast. Not only that, it was accompanied by very high impact weather events. So during this period, exceptional heavy rain events, the number of frequency of exceptional heavy rain events were very high. So this is just a clipping from Times of India to show that in the last 8 decades, in the last 10 years, they showed that there were only 8 extreme rainfall system, of which 2019 saw 5 extreme rainfall events alone, and there was extensive flooding. So what we did was we tried to understand how this coupling happened in 2019. So for that, we took these two subdivisions, these two states, Gujarat and Maharashtra, where there was extensive flooding, and we counted the heavy rainfall stations that reported the heavy to extreme rainfall. And we decided a threshold based on, we wanted to see organized systems, the heavy precipitating systems. So what we did was when we looked into it, we saw that these events were not very like single day events. They happened in spells, they happened in episodes. There were episodic increase and decrease in the station that received heavy rainfall during this year. So we had 3 different distinct heavy rainfall spells. And when we looked into the GPM data, when we counted the grids of heavy rainfall in the GPM, we found that this heavy rainfall, which we saw in Western India from station observations, was not a very localized event. It happened across the entire South Asian subcontinent. It extended from South Asia to Southeast Asia till the South China Sea. So it shows that this was a very organized event that was happening. And on looking into the snapshots of the GPM spectral latent heating profile, so we looked into all the passes during this intense rainfall event, we find that the heating peak, the black color here is the mean heating peak from all the passes that we obtained. So it shows that the heating peak is at 8 kilometers. We have a lower peak from the convective, but the maximum heating occurs at 8 kilometers, which shows that this top heavy heating is due to abundant stratiform precipitation that is occurring from the precipitating systems over this region. Now, this is going back to the same thing, just to say that if we have a top-heavy heating, we have a very intense mid-level circulation. So when we looked into the mid-level circulation, the PV, the potential vorticity, the relative vorticity, we find this is the relative vorticity from the station pattern. The station numbers were regressed. So the relative vorticity during this intense episodes, these 3 intense episodes, shows that there is an east-west elongated oriented maxima of relative vorticity, which extends from the Arabian Sea, North Arabian Sea, this Gujarat, Maharashtra region, where we see the maxima, and it extends across South China Sea with a very large, intense cyclonic circulation. And when we look into the vertical cross-section, this is the vertical cross-section across the Gujarat and the Maharashtra region, we see that the potential vorticities, because we have a very strong heating gradient from the stratiform precipitating system, there is a generation. So where this heating gradient, it generates PV. So there is a generation of PV at the mid to upper tropospheric levels, which basically sets a favorable environment for vertical velocities. The contours here are the vertical velocities. We have very high vertical velocity due to this PV that has been generated. And this high PV at mid levels, it promotes the development of further deep convection. So basically we had this stratiform heating, which gave us the gradient. This generates the PV, which further enhances the upward motion and sets a feedback system wherein it favors the further growth of the further sustenance of the tropical systems. Now, if we look into the OLR and the moisture transport, we find that again, the deep convection, the OLR, it extends across this entire region, which shows that deep convection is occurring over the entire region. And the moisture transport, it shows that the moisture, due to the SST gradient that is set up by the Indian Ocean dipole, there is transfer of moisture from the equatorial Indian Ocean into the Western Indian region, which feeds these deep convective systems and helps in growth of deep convection, which sustains the circulation and keeps the feedback. So, and this convergence and divergence, this is maintained across this entire season with this episodic increase. So this stratiform heating, we find that it forces a Rossby wave response, the cyclonic circulation, that is a Rossby wave response, and it stretches across South and Southeast Asia, which sustains this widespread monsoon, heavy to extreme rainfall events over this entire region. And accordingly, we see that there is high precipitable water, which is seen from, this is the right side, we have the precipitable water. So we have this depletion of moisture from equatorial Indian Ocean and the accumulation of moisture, which favors deep convection over this region. And this is not a one-of-a-kind event. So we checked for other years also. So we found that when we counted the heavy rainfall over Western India, we find that the IOD years, which are not accompanied by El Nino, stands out. So we have more heavy rainfall, heavy precipitating systems, which have more stratiform type of convection during these IOD events, which are very strong IOD events like 61, 94, 2006, 2019. So basically what happens is the heating gradient in the equatorial region, it sets up a Rossby wave type of response, equatorial Rossby wave from the cooling. And you can see this, there is an anticyclone, the dual anticyclone here and this equatorial region, southern equatorial region. So northern part of the anticyclone, it strengthens the flow into the Western India where we have the vortex. And the moisture influx here, it builds the systems, it sustains the system, which gives us a Rossby wave response over this region and gives us this extensive cyclonic anomaly over this region. Now, there is a feedback going on, but what happens in the climate models? The climate models, it's a key challenge. This vertical heating, we already know the vertical variation of heating is very important for our region. But the climate models and the weather models, they are not able to simulate this vertical structure of heating. So this is a paper by T. N. Krishnamurthy where he showed that different ensemble members and even their ensemble mean. So this violet is the ensemble mean. We can see that this ensemble mean is not able to simulate the vertical profiles that is observed by TRMM. So in an atmospheric model, we have large errors in the vertical structure, which leads to errors in the convergence and the divergence center. So this leads to erroneous circulations, large biases in the circulation, and in turn leads to large biases in the precipitation. So I'd like to conclude by saying that over the monsoon region, the circulation is convectively coupled large-scale phenomena. And these tropical cloud clusters, what we call as mesoscale convective systems, they provide an important link between the atmospheric convection and the large-scale circulation. And these heavy precipitating systems, which are embedded within this large-scale circulation, it by itself has complex feedbacks between the circulation, the moisture available, the vertical profile of the winds, the heating fields at very different spatial time scales. So we go from meso to synoptic to large scale. So all the scales are interacting together. And it is a very challenging problem to deal with in a model. And over our region, the top heavy stratiform heating is very important. So we need to understand our system. This heating is very critical driver for the metropospheric circulation, which in turn affects the lower level and the upper level circulation. So this vorticity stretching that occurs across the continental scale region from the peninsular region as well as the Southeast Asia, and it provides a condition for occurrence of extreme precipitation. Along with that, along with this complexity, we have the climate modes like the IOD and so La Nina. So these climate modes of variability, they reinforce the cross-equatorial moisture transport or they deplete the moisture transport. Depending on that, the deep convection, occurrence of deep convection changes. So sometimes it favors stratiform systems, sometimes it does not favor, depending on the circulation will change. And as we go to a changing climate, as the global warming happens further, these type of systems will change. So we need to really model these types of systems better in our model. Currently, our models does not capture these systems properly. They have biases in the latent heating, which leads to biases in the monsoon dynamics like the synoptic systems or the large scale. So I would like to end by saying that we need multi-platform observational networks as well as diagnostic studies, process-level diagnostic studies, along with new methodologies like, as Brian was telling in the morning, that we need to use the plethora of data that is available from satellite images based on AI/ML methods and go to kilometer scale modeling to better capture the mesoscale organization, the large scale organization. It is not a single mesoscale system that is happening. There is a large scale organization across thousands of kilometers and its interaction from meso to synoptic to large scale to better predict and project the South Asian precipitation. Thank you. Hello. Hello, I am unable to hear actually.
Very nice presentation, Ayantika. Very nice summary of yeah.
Thank you for your impressive presentation, Dr. Ayantika. Now it is open for discussion. Let us have questions from the participants. First from the offline participants from the auditorium, then from the online participants. So the first question will be within 10 seconds. You can go ahead and ask in that microphone.
Am I audible?
Yeah, I can hear you.
It was a nice presentation. I just have two queries from your side. Like you have been talking about the relation between this convection and the precipitation, right? Like you defined based upon your outgoing long wave radiation, and then you have talked about the precipitation index. Like precipitation, how much it varies with the deep convection.
Exactly. Not exactly outgoing long wave. We are doing it based on the latent heating, because in the tropical system, the over the monsoon region, this latent heating has a direct interaction. We have not put the long wave there.
I have seen, but to most of your you have two figures which were showing that cool are less than 200 watts per meter square, and you're trying to relate it with the precipitations. You had two maps, right? 2 or 3. Like how you were.
That was for only the latent heating. We don't have the long wave in that.
Okay, it's only for the latent heating. Okay, it was showing
They
that.
put the long wave. Actually, there are studies that have put the long wave. It enhances the effect. So it further intensifies.
Okay, because you were talking about mostly the western region, which we are talking about the deep convection. I'm not sure what is your threshold for defining a deep convection, like the height wise. I'm asking, what is the vertical extent that you talk in terms of deep convection?
See, we have not defined deep convection based on the height. What we have done is, when we design this experiment, we take the surface rain rate, and then we have station observations, which gives us the vertical profiles of latent heating, and we distribute that rain rate in the vertical profiles. Okay, so it extends till.
Yeah, because most of the radar observations over the western Ghats and the southern, like almost the monsoon regions, what we mostly get is the consistence of the shallow terms of precipitation only during this monsoon convection. So that's why I doubt that whether the deep what you're talking about is in terms of that or the otherwise. Because observations are the most important. Whether you go towards the Bay of Bengal, the other side, the head Bay of Bengal, where you get the maximum convection, or when you talk about the western Ghats, most of the radar observation shows that they are mostly dominated by the congestive type of precipitation rather than the deep convection precipitation.
Yeah, actually, if you take a look from this TRMM and GPM, so the profiles that we obtain, based on that, they deduce the latent heating. So we have used that latent heating, not from this observed what you are getting from ground-based radars.
Okay, I think I will have that discussion later, because my question was not properly interpreted.
Yeah.
Good afternoon, Andrea. Hello. Yeah, are we audible?
I am actually, the voice is not coming through. Can you say something now? Yeah.
Hello.
Yeah, now it's audible. Yeah.
I think what in connection with what Uma was telling, because in one of the slides, Rajiv sir was also showing a double mode structure of heating structure, right? Which is composed of both shallow plus deep.
Yeah.
Two maximum heating, one below the melting layer and one around 8 kilometers. Those type of double structure formed over the west coast, most of the monsoon period. So I think was telling about that. It's very hard to represent those.
It is there, yeah, and it depends on how much of heavy precipitation. So sometimes it is always a double structures. True, that is there. I agree to that. Sometimes the upper, yeah.
The model cannot capture that double structures. That is the problem. Even TRMM also.
Yeah, if the climate models and the weather models don't capture that double structure, no, not really.
Thank you, Dr. Antika, for the informative presentation. It was both insightful and engaging. Now I would like to invite Dr. Rashmi EA, our second panelist. Dr. Rashmi EA, Scientist E, Group Head, Atmospheric Science Group, ANSYS, is engaged in frontline research in cloud microphysics for improving the accuracy of precipitation estimation in complex regions like Western Ghat provinces of peninsular India. She has been instrumental in setting up a high-altitude cloud physics laboratory at Rajmale, Munnar, and upgradation of Brehmur Observatory in Trivandrum. She also contributed immensely to the establishment of lightning detection network in the south coast of India in collaboration with IITM and IMD. Dr. Rashmi and her colleagues were able to bring out clearly the cedar feeder mechanism in the southern Western Ghats regions during the monsoon season. She has also worked in the area of air quality monitoring and is diurnal cycle over a coastal location as part of modeling air pollution and networking program of MOES. She is a recipient of Certificate of Merit in 2020 by MOES. Dr. Rashmi will talk on the precipitation microphysics in organized microscale systems, mesoscale systems, the role of warm clouds.
Everybody, I extend thanks for letting me and for the nice introduction. And I'll be discussing on the precipitation microphysics in organized mesoscale system and the role of warm clouds. So I'm moving ahead with a little bit introduction of the system of what is meant by warm clouds. Warm clouds is a cloud droplets that consist of entirely tiny droplet that is grow by the condensation onto the aerosol particles. And the aerosol, that is also aerosol particle that depends upon the changes in the humidity, depending on the chemical composition. The properties of the aerosol particles also determine the growth of the warm clouds. And the droplets, which is essentially formed through the process of collision and coalescence. So the accurate representation, as earlier presenters has pointed out very well, the accurate representation of these warm clouds in the numerical model is still a challenging problem because it induces uncertainties in the climate projections as well as in the estimation of the rain rates. So this is a very schematic diagram. So Rajiv sir said that the feedback process is very much important. So the line which is shown over here, it's a two-way feedback process. So essentially we consider the water vapor and it forms the condensation process, forms the CCN and forms the cloud water, and we are waiting. You can concentrate on the red line. And it forms the warm rain. And the warm rain, essentially two-way feedback process, it again contributes to the cloud ISO, QI process also. So the process, because it's an interrelated microphysical processes that exist in the atmosphere that is contributing to the total surface precipitation, and it also determines the down below black color interface shows the surface precipitation. So how this warm rain as well as the ice crystal process are contributing to the surface precipitation, and what is the numerical challenges existing in the model that has been schematically shown over here. So I am just touching upon the high altitude observatory that is established by the MOES, and this is the pictorial representation, the heavily instrumented site where this list of instruments are being installed over the site. And Dr. Rajiv and Dr. Tara madam was online, and both of them are quite instrumental in setting up the observation site or the high altitude observation site. They have have given the guidelines of the scientific objective and what sort of instrument to be augmented at the site so as to study the cloud microphysical processes in details. So I'll be presenting two of the research work carried out with PhD students from this measurements carried from this site. So again, I would like to present a precipitation microphysics in organized mesoscale system. So as we aware about the Kerala flood of 2018 and 19, the site is recorded in both the 2018 as well as in 19 around 400 above millimeter rainfall in August 14, 15 and 16 and 8th August 2019. So there are literatures that already shown that both the events are supported by the organized mesoscale system favored by the depression formed in the Bay of Bengal. So that is Vishwanath Pillai, and there are many studies, Hunt, Menon et al. And there are many studies, and Vijay Kumar has already shown the presence of the organized mesoscale structure contributing to the precipitation. So my job is to give an evidence to the ground observed microphysics part, how the microphysics part was engaged in this precipitation system. So here you can see the pointer. Okay. So here the left panel shows the 14, 15 and 16 August 2018 flood case, and right panel shows the 8th August, and it's top panel shows the reflectivity and fall velocity, gradient in fall velocity and rainwater content. So you can see the topmost panel reflectivity at 4.8 kilometer. You can see the changes in the reflectivity pattern. So that it clearly suggests that there is stratiform precipitation that is causing the at the precipitation level, and a clear gradients in the fall velocity also. So the signal is clearly seen that stratiform precipitation has been occurred over this 2018 and as well as in 19. But 2018 on 15, if you the down below the rainwater content, you can see the rainwater content in 2019 was quite higher as compared to 2018. So what it was, why it is so? It is so means the drop size distribution from the ground observation. So this I am projecting the observations from micro rain radar as well as micro rain radar observation. So it shows that the ground-based instrument which gives a clear evidence of the drop size distribution, which is higher in drop size distribution, and that is giving more rainwater content at the ground level. That is giving a more contributing to the top surface precipitation during this scenario. So there's a clear evidence that we are projecting through the from this observation. At the microphysical, next graph is showing the drop size distribution from the ground using the micro rain radar observation, and from 14, 15 and 16, and last panel for 8th August. And the right panel shows the sigma mean diameter class and the standard deviation. So this also shows, you can see the dip in the diameter class at the top panel figure A, where and the corresponding dip in the mean diameter and the standard deviation at the maybe around 18 LST. You can see the IST, you can see the dip in the diameter class as well as on the mean diameter as well as sigma. So these variations actually suggest this. So I'm not detailing the graph. It actually says that when you have a precipitation system, when you have a drop size distribution at your hand, there is two processes taking place. One is size controlled and number controlled process. These two processes. So when the size is getting enhanced, keeping the number concentration as same, it is we says that it is a number controlled process. When size is not changing, but number is changing, the drop size remains 2 mm, 3 mm, or 4 mm, or it between 1 to 2 mm diameter class. But the number concentration of the drops, small drops, it is getting enhanced. So means the size, it is a size controlled process, but number is enhancing. So these two processes happening within the cloud system, that can be evidently examined using this observation. So it is the process that
lies in the cloud system at the mostly in the precipitation scenario below the 4 km, below the freezing level. This kind of process do exist, and that is attributing to the higher precipitation rate during this. So when such kind of a heavy precipitation system occurs in the Western Ghats or any other parts of the place, we can see that this kind of this is called one of the facets of the stratiform precipitation, that we can see that one more thing, the role of warm clouds. I am just going ahead with that, where you can see when this number controlled size controlled process occurring at the 4 km or 3 km in the above the layer, because of the Western Ghats orography, we will have always a layer of low level clouds at the surface. So these low level clouds which is present over the Western Ghats act as favoring the mechanism which is happening at the topmost layer. So both the way this process will mutually feedback process will take place, and that will also enhance the precipitation. Those features are summarized in this paper, and this is a PhD work. So then I'm moving about the warm cloud formation. This one example I have shown over here, when a mesoscale process system has very prominent during the monsoon system, how the cloud microphysical process is giving the evidences. Next is the rain. Next I'm coming to the warm clouds process and formation process. That's most of the stratiform or shallow precipitation, which is happening in a warm clouds less than 30 minutes of duration. This is from book. It's written by Ferram, 2015. And one of the using radar observation, Suganya and Kalpuredi 2022, I think they have installed the radar in Mandra Day. From that observation, less than 25% of the warm clouds result to moderate, light to moderate rain. So these warm clouds which here, how it is giving a moderate rain. Nowadays, how it is giving to a more beyond moderate rain, how this warm clouds are giving a higher precipitation. And they have also concluded that 28% of the total accumulated precipitation is also contributed by the warm cloud system or a shallow cloud system. So these are the reality that has been reported using the ground observation. But the challenge keeping the table for the researchers and the students is to accommodate this process, low clouds, and difficult to represent in the cloud models. And this is a schematic diagram is showing the collision and coalescence process. This is a Gambar et al. 2024. It's a part of collaborative work with IIT, I guess. And it's a research aircraft observation, and you can see the research aircraft passing through the cumulus congestus clouds. And you can the top you can see the large scale micro scale eddy and a smaller eddy, and that is cascading to a much droplet eddy. So energy cascading, when a cloud system exists either in shallow or cumulus congestus form, energy decaying process happening through a multiple vortex. It is being created a multiple through the vortex mechanism. So that has been explained through the numerical simulation, as well as the given the observed results are given in this paper. And moving on to the on the warm rain process, how difficult it was to identify the warm rain process. So TRM precipitation earlier, Schumacher and House 2003, they have identified, we can see that it's a convective precipitation and a stratiform precipitation and total rain rate. What is happening in the stratiform precipitation again? So they have made an effort to modify the algorithm in the TRMF and identify the shallow and isolated echoes. So that because most of the shallow and isolated echo are added to the stratiform echo and giving the total precipitation. So a misaccurate rainfall information is coming out of this result. So modify the algorithm, identify the shallow echo has been efforted by this paper. Then again to the shallow or warm cloud process. As Rajiv sir in the morning presentation, we have seen that it is very difficult to penetrate look the warm cloud or shallow echo from the top of the atmosphere or from the satellite, because it gives
the top of the atmosphere observation only. So, Anuradhan and Bhav's 2017 have proposed a comprehensive using the satellite as well as using the ground observation, how we can capture the shallow precipitation detection mechanism. It's a methodology driven by the detection mechanism, so that a single entity is not will not surface will not be able to capture the shallow precipitation echoes. So by this method, they have identified that the down panel you can see deep, transition, and shallow. So by this comprehensive method, they have proposing to identify the shallow echo properly and to derive the microphysical properties or the rain or snow or the water accumulation process they have derived through. So over the Indian region, moving on to the another research work by Kumar et al. In 2018. This is entirely using TRMM observations over the tropics from 30° north to 30° south. It's also identified the shallow echo during the monsoon season. So that is also again on the reflectivity factor. To identify the shallow echo, they have approached the method of 0.75 kilometer area widespread and below the freezing level. So this method has been adopted widely to identify the shallow echo. So based on this knowledge and the comprehensive understanding, we also tried to identify the shallow echo. So we from our observatory, we are also using the micro rain radar, distrometer, and ceilometer observation. So we also made an objective methodology to identify the shallow echo, how the shallow echo can be identified. So you can see, see the micro rain radar reflectivity measurement, top panel and below 3 panel. You can see the very isolated shallow echo where the top height is less than. We have strictly followed the top height should be less than 4 kilometers. 0° isotherm level, so that we can identify it. So you can see in the last panel very well-defined bright band structure, well-defined precipitation system you can see in the bottom panel. But to avoid that, this shallow echo we have identified. This shallow echoes are associated with precipitation. Shallow echoes in the atmosphere are very suspended, but it is not precipitate. It is but here we have chosen to identify the temporary echo associated with the precipitation patterns only. So here that estimation has continued, identified the shallow echo and identified that shallow echo has been again classified into 5 to 20, because earlier I have shown the literature. Most of the shallow echo lasting for less than 30 minutes. But here from the ground observation, there are shallow echo that is being sustained in the atmosphere more than 40 minutes, and giving to light different classes of rain rate, light, moderate, and heavy. So how this shallow? This is I am giving. This is not a answer to the question. I am giving there is more work can be done on this aspect. How a shallow echo is sustaining more than beyond 40 minutes, and how it is sustaining giving a and then the last panel, you can see that it is giving light rain, acceptable. It is giving moderate rain, okay. But how it is contributing to the heavy rain pattern. A shallow echo exists in the atmosphere. Some also, and we can see during all these findings, we have a ceilometer observation. So we plotted the ceilometer observation at the ground level, and you can see the white rectangle, the time of the precipitation where the shallow echo, as well as the ceilometer observation. So we can see the clouds are nearly close to within the boundary layer, nearly 1 kilometer level, 800 meter level, or 2 kilometer level. Left panel shows the little elevated cloud layer. So that part I'm not touching. But my point is that you have a shallow echo, and that is giving a high precipitation, and how it is giving a high amount of precipitation, and how it's sustaining for more than 40 minutes. So DST, this is a microphysical part also we have done. That also giving a clear signature. There is a higher diameter class exists in the shallow echo, and it is here in the last panel, you can see, and F panel, you can see shallow echo sustained for more than 60 minutes. So, and the corresponding microphysical part, liquid water content and mean diameter class, number concentration, and liquid water content also we have presented. So the microphysical part also examined Both the partners suggested that this echoes can last for 5 to 10 minutes and mostly it is 5 to 10 minutes or less than 20 minutes. But there are echoes which is sustained to beyond. And in an organized precipitating system, like in the monsoon system, in a wet and dry scenario cases, still we can see the echoes in the, so it's a very clustered. In wet and dry spell, the star denotes the first layer of cloud, second layer of cloud, and third layer of, so two layering of clouds. And it's a rain rate on the x-axis, duration on the y-axis. So in the monsoon time, we can see the different layering of cloud. That's why it has been quite distributed. A star and a rectangle have been quietly distributed at different duration level. So it exists a higher duration time. The point is it exists a higher duration and it is giving a more higher rain rate and due to the presence of different layering of clouds. That is the pictorial representation is provided in this graph. So the analysis is carried out by research student Anusha Andrews, and I'm thankful to her there because it's a very difficult process to identify the shallow echo from this clustered, to identify each and every pixel and to delineate the microphysical process, a very difficult process, and that has been published. So I've concluded that my presentation over here saying that still we have not really understood the process of the shallow echo, how it is converted from shallow to light to moderate or giving a high echo, and what is the conversion process exists even below the melting layer. I'm not confusing with the cloud water. If you go the microphysics process beyond the whole scenario is more feedback process will come. But here we have a very small system, but still we are not able to fully capture the process within the system, even microphysically as well as true numerically. So we have a very more job to do. With that, I conclude my presentation. Thank you.
Thank you, Dr. Lakshmi, for your nice presentation with clarity. Now the presentation material is open for discussion. I invite a few questions from the auditorium for the offline participants, followed by the question from the online participants. And those who are asking questions from the auditorium are requested to come forward so that the discussion can be benefited to online participants also. Any question? Yes, Dr. Jayakumar. If you don't like,
this mostly the discussion the expression of the problems which is mentioning in observation.
Not really, because we need to work on the auto conversion process of the cloud to rainwater or rainwater. The processes are mostly, I would say, for shallow convection. The main physical process is that when shallow conversion are feeding to the large scale system, shallow convection occurs, and the shallow convective clouds are formed within the boundary layer. We do not know those processes. And shallow convection convective boundary layer, and there are theoretical and studies cyclone LCL level where clouds have started forming in. So that also we don't know. So all this process are unable to comprehend through the model as well as in the auto conversion process. So we have many things. Thank you.
Very nice presentation. I just have one thing, because you have ready to understand the complete physical process, whether with respect to the draw diameters and all of the things, and you even in fact found that very large diameter exists well and near 5 kilometers. What should be because you have missed the dynamics part.
Yes.
What do you feel that how you will be able to accommodate it and understand? Because I think if this is the case, then the dynamics must be the main role that is
Yes.
holding that particular meter. Because such a graph, right, was not going above and then
Yes, very correct, madam, because the large scale part plays a key role, and plus the regional factors. Because what I have presented, one site location is the Toronto, it's a little elevated area, 400 meter above mean sea level, where the clouds are forming near close to the surface, not maybe within 1 kilometer level. So that 1 kilometer level, the clouds started forming during the monsoon season, and that is creating that is helping the formation of the shallow system, and that is favoring the formation of the mesoscale as well as the deep convective core also. So that one part is that is regional, as I would say, regional plan during the monsoon, regional part. Then monsoon, we have a large scale system and a moisture supply, and that also helping the formation of the multi-layering of the clouds. So the multi-layering of the clouds occurs in a different layers in the atmosphere. The shallow clouds actually favoring the formation of these other clouds as well. So regional factors as well as the monsoon dynamics, all these factors plays a key role in the formation of the shallow cloud systems and ultimately the precipitation.
Any other question? We have sufficient time. Questions from the students? Any question from online?
So thank you everyone, and this work carried out by research student also, and extend thanks to the organizers and Dr. Abhilash also inviting me. Thank you.
Thank you, Dr. Rashmi, for the informative talk. It provided valuable insight in a concise manner. As a token of appreciation, I invite Dr. Professor Babu, C.A. Babu, to present a memento to Dr. Rashmi. With this, we have come to the end of this panel discussion. We'll convene after lunch at 2 p.m. again in this hall. 1:50. We'll convene at 1:50. Lunch is provided in the fifth floor. എന്റെ മേലെ അയച്ചേക്കല്ല സാറിനും എനിക്കും കൂടെ അയച്ചതായിരുന്നു. ഇല്ല, ജയകുമാർ അയച്ചത്. ഞാൻ ഇതിനെ ഫോർവേഡ് ചെയ്താക്കിയത്.
ചേട്ടാ ഒന്ന് വന്നാട്ടാ ചേട്ടാ നിവേദ ഓൺലൈൻ ഉണ്ടോ? അകത്തേക്ക് പോ സ്റ്റെഫി 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 മേളിലേക്ക് പോയാൽ മതി കയറിയിട്ട് എന്നിട്ട് ഞാൻ അവിടെ നിന്ന് പറയാം.
ആ മെയിലൊന്നും ഞാൻ ഫോർവേഡ് ചെയ്തിട്ടുണ്ട്.